The vast expanse of space is generally considered a realm of order, a silent, systematic domain governed by gravity, where celestial mechanics operate with unyielding predictability. Yet, in November of the year 2025, an anomaly shattered this perception. An interstellar traveler designated 3 Atlas, a celestial body barely the size of a sizable mountain, unexpectedly began to increase its velocity. This acceleration was not accompanied by any visible propellant expulsion, outgassing, or any discernible cause. Concurrently, the sun unleashed a torrent of intense solar flares, causing Earth's magnetic shield to vibrate. Amidst this celestial upheaval, scientist Stephen Burns articulated a somber premonition. A significant wave is approaching. 2 distinct events converging at a single point in time. Were these mere coincidences, or was there a deliberate orchestration at play? Comets typically exhibit erratic behavior. They sputter, they wobble, they diminish in intensity. However, 3 Atlas deviates from this norm. Its trajectory is remarkably smooth, precise, and eerily programmed. Consequently, our investigation tonight will trace its silent journey through the cosmic darkness to probe a question that could fundamentally redefine our understanding of the natural world. If 3 Atlas is indeed a comet, as some would have us believe, then why is it exhibiting characteristics of a spacecraft that has just reawakened to its programmed objective? Should this profound mystery continue to captivate your interest, as it has mine, please ensure you engage the like button and subscribe to our channel to remain abreast of every development as this extraordinary narrative unfolds in real time. Share your thoughts in the comments section. Indicate your location, the current time there, and whether you feel we are being presented with the complete truth regarding these world-altering revelations. Furthermore, if you wish to contribute to the expansion of our community, please share this video across platforms like X, Facebook, Reddit, or even within your personal group chats. Your support is invaluable, enabling us to continue pursuing and uncovering stories of this magnitude. We extend our sincere gratitude for your unwavering backing. Part 1 delves into a breakthrough alert, specifically focusing on the inexplicable propulsion of 3 Atlas. Something is amiss in the outer reaches of our solar system, a truth that many are hesitant to vocalize. In November of 2025, astronomers diligently observing the interstellar object known as 3I Atlas, also catalogued as C5N1, detected a phenomenon that defied conventional astronomical understanding. The object was not merely proceeding along its predicted course, it was actively accelerating, gaining speed in a manner that could not be attributed to gravitational forces alone. These crucial data points were derived from NASA's Jet Propulsion Laboratory Horizon System, the sophisticated computational framework responsible for the precise tracking of everything from artificial satellites to near-Earth asteroids. The information yielded by this system painted a picture that caused considerable disquiet among physicists. The observed acceleration was dissected into 3 distinct components, designated A1, A2, and A3. These can be conceptualized as vectors representing the directions in which a force is propelling the object. The A1 component, representing the radial force pushing either towards or away from the Sun, measured approximately 1.662 multiplied by 10 to the -6th astronomical units per day squared. The A2 component, indicating the tangential force acting along the object's direction of travel, was recorded at roughly 7.089089 multiplied by 10 to the -7th astronomical units per day squared. The A3 component, representing the out-of-plane force, registered as precisely 0, a value that was both measurable and, seemingly, impossible. To grasp the significance of these figures, it is essential to comprehend their underlying context. When astronomers track comets, they frequently observe deviations from purely gravitational motion, often attributed to non-gravitational forces. Comets, being icy bodies, experience sublimation as they approach the sun, releasing gas and dust into space. This expulsion generates a thrust, akin to a leaking pressurized container propelling itself through the void. These jets nudge the comet off its predictable gravitational path. However, the nature of gas and dust expulsion from a rotating, irregularly shaped mass of ice and rock is inherently chaotic. Jets erupt in multiple directions, the nucleus tumbles, and the surface is uneven. This results in thrust components acting in all three dimensions: radial, tangential, and, crucially, out of the orbital plane. In stark contrast, 3I Atlas displayed none of this disorder. Its propulsive force was confined exclusively within the orbital plane, as if its movement had been meticulously programmed to operate in only two dimensions, completely disregarding the third. Over a period of approximately 20 days, this sustained acceleration resulted in a velocity alteration of about 60 meters per second. This is not a negligible effect. It represents a genuine and persistent force that should manifest visible evidence. Yet, observers scanning for such indications found nothing. No new celestial body had appeared nearby. No luminous tail trailed the object. High-resolution imagery revealed no discernible jets. To all appearances, the object seemed inert. Its apparent magnitude remained consistently between 14.7 and 14.9, exhibiting minimal fluctuation. It did not brighten in the manner expected of a comet awakening as it neared the sun. It was not fragmenting, nor was it visibly shedding material. It simply accelerated silently and with pinpoint accuracy within a confined plane. Envision observing a boat gliding across a lake devoid of any engine, sails, or oars. The water behind it displays no wake, yet the vessel steadily gains speed, traversing in a perfectly straight line as if guided by unseen tracks. Such a scenario would undoubtedly prompt significant questions. The central inquiry concerning 3 Atlas is thus, if it is merely a comet, why is it behaving like a spacecraft? The implications of this situation extend far beyond the trajectory of a single peculiar celestial body traversing our solar system. If conventional explanations falter, if we exhaust every conceivable mechanism provided by physics and chemistry, we are left with two stark possibilities. Either we are witnessing an unprecedented exotic phenomenon that current scientific understanding cannot account for, or we are observing something demonstrably engineered. Both scenarios necessitate a radical revision of our established knowledge regarding interstellar objects. Both carry profound implications for our comprehension of solar system dynamics, the fundamental nature of matter traveling between stars, and indeed, the unsettling question of our cosmic solitude. Around the same period that 3 Atlas commenced its anomalous acceleration, geophysicist Stephen Burns issued a grave warning, asserting that Earth was entering a significant phase of heightened energetic activity. Solar flares were escalating in intensity, geomagnetic storms were buffeting the planet's protective magnetic field, and seismic events were occurring in unusual clusters. Burns highlighted a confluence of factors: a 28-day recurring cycle of coronal holes on the sun, the peak of the Taurid meteor shower in early November, a supermoon event on November 5th, and upcoming planetary alignments. His contention was that these were not isolated occurrences, but integral components of a larger pattern, an escalating crescendo of cosmic energy manifesting across multiple systems. The temporal coincidence is particularly intriguing. An interstellar visitor exhibiting inexplicable behavior precisely when our sun and planet appear to be intensifying their energetic output. Coincidences, of course, are a natural part of the universe's vastness, where events frequently overlap without any inherent connection. However, when confronted with anomalies, coincidences begin to resemble significant clues, subtly suggesting that a broader, perhaps overlooked context might be at play. This presentation will meticulously examine the evidence, the anomalies, and the proposed hypotheses, both natural and unconventional. We will scrutinize the data that has unnerved scientists and explore the challenges encountered when attempting to reconcile the behavior of 3 Atlas with established models of cometary physics, observing how these models strain under the imposed pressure. We will consider alternative explanations that may sound like science fiction, but could potentially represent scientific reality. Furthermore, we will contextualize this object within the framework of other interstellar visitors, the dynamic energetic environment of our solar system, and the cutting-edge discoveries that are reshaping our understanding of small celestial bodies and fundamental physical laws. Ultimately, we will pose the question that, at present, many are reluctant to articulate too loudly. What if this object is not merely a comet, but rather a harbinger of something far more significant? Time, zero point 0.5 seconds. Part 2 focuses on the fundamental significance of the A3 equaling zero condition. Let us first examine the typical eccentricities of cometary behavior. Understanding what is considered normal will illuminate precisely why 3 Atlas stands apart as an extraordinary anomaly. As a comet approaches the sun, solar radiation warms its surface. The ice undergoes sublimation, transitioning directly from a solid to a gaseous state without passing through a liquid phase. This process generates jets of vapor that carry dust particles along with them. These jets are expelled through vents or fissures in the comet's nucleus. The direction of the resulting thrust vector varies depending on the location of these vents and the orientation of the nucleus at any given moment. The nucleus is almost certainly in a state of rotation, tumbling through space along a complex axis. As it spins, different vents are exposed to solar radiation at different intervals. The outcome is a thrust vector that traverses three-dimensional space, impelling the comet radially, tangentially, and off the plane of its orbit. The majority of comets exhibit significant out-of-plane acceleration. The A3 component is seldom zero because the processes involved are inherently chaotic. Surface features are diverse, rotational states are complex, and the timing of vent activation is influenced by thermal conductivity, subsurface structure, and the distribution of volatile compounds, all of which vary across different regions of the surface. Consequently, thrust is generated in upward, downward, and sideways directions, in combinations that shift as the comet rotates and as solar heating intensity fluctuates with distance. Orbital modelers tasked with tracking these objects routinely incorporate all 3 components because the observational data demands it. Statistical analyses of cometary non-gravitational forces clearly demonstrate this pattern. When examining dozens or even hundreds of comets, the distribution of A3 values spans a wide range. Some comets display minor out-of-plane components, while others exhibit substantial ones. However, a value of exactly zero is exceedingly rare. It is possible to observe an A3 value close to zero under conditions of a short observation period or weak acceleration. But when sustained acceleration occurs over weeks with a robust observational baseline, an A3 value of zero becomes a definitive statement, indicating that the propulsive force is tightly controlled, confined, and aligned with a single plane. Within the margin of error for the JPL Horizon's orbital fit, 3 Atlas returned an A3 value of zero. The residuals, which represent the minute discrepancies between the object's predicted position and its actual observed location, do not necessitate the inclusion of any out-of-plane component. The orbital fit functions effectively without it. This outcome is not an artifact of insufficient data. The observational coverage spanned multiple sites over an extended period, and the astrometric precision was exceptionally high. Had there been a meaningful out-of-plane thrust, the orbital model would have detected it. Therefore, what is the implication of an object accelerating for 20 days without deviating from its orbital plane? It suggests that the mechanism generating this thrust is either remarkably stable or exceptionally precise. For natural outgassing to achieve such a result, the nucleus would need to possess a configuration where jets expel material solely in directions lying within the orbital plane, never perpendicular to it. This would require a nucleus shaped in a very specific manner, oriented in a particular way, with vents positioned such that their combined thrust effectively cancels out any perpendicular component while simultaneously reinforcing the radial and tangential components. While not entirely impossible, this scenario demands a level of geometric precision that is rarely observed in nature. One proposed hypothesis involves uniform vent distribution. If the nucleus is studded with numerous small vents spread evenly across its surface, and if these vents expel material at comparable rates, the individual thrust vectors might combine to produce a net force that coincidentally lies within the orbital plane. The operative word here is coincidentally. This scenario necessitates that the nucleus's axis of rotation aligns in a highly specific manner with the orbital plane, ideally perpendicular to it, so that as the nucleus spins, vents on all sides expel material symmetrically. Furthermore, the surface composition must be sufficiently uniform to prevent any single hemisphere from dominating the outgassing process. Similarly, thermal conductivity must be consistent to avoid localized hotspots with enhanced venting. While each of these conditions is plausible in isolation, their collective convergence points to a highly improbable configuration. Another hypothesis centers on an unusual volatile composition. It is possible that 3 Atlas is exceptionally rich in highly volatile ices, such as carbon monoxide, carbon dioxide, or molecular nitrogen. These substances sublimate at lower temperatures and are ejected at higher velocities than water ice. High-velocity expulsion translates to greater thrust for a given mass of expelled material, potentially explaining the acceleration without a prominent coma. However, this explanation still fails to address the confinement to the orbital plane. Gas jets emanating from a rotating body should inherently possess out-of-plane components, unless the spin axis and vent geometry conspire in a highly specific manner. A third possibility is micro-outgassing, where minuscule jets eject particles at high speeds, but in quantities too small to be resolved by current telescopic capabilities. This might account for the absence of a visible coma, but it does not resolve the A3 problem. Microjets, too, should exhibit directional variations as the nucleus rotates, generating some out-of-plane thrust, unless the system possesses remarkable symmetry. The condition of zero A3 thrust opens the door to more unconventional interpretations. If one were designing a propulsion system for a small spacecraft, the objective would be to maintain thrust alignment with the trajectory, avoiding any propellant expenditure directed perpendicular to the intended motion. Engines would be fired within the orbital plane to efficiently adjust speed and direction. A propulsion profile that is perfectly confined to the orbital plane is precisely what one would expect from a controlled propulsion system. This does not definitively prove that 3I Atlas is a spacecraft. Rather, it suggests that the observed thrust signature is more consistent with active control than with passive, chaotic outgassing. It is a piece of evidence that fits more congruously into one explanatory framework than another, even if that framework is unsettling. Consider the alternative. If 3 Atlas is outgassing naturally, then we are witnessing a cosmic alignment of geometry, composition, rotational state, and timing so extraordinarily precise that it mimics artificial behavior. While nature can indeed be surprising, it rarely presents itself with such meticulous tidiness. If there is no discernible outgassing or tail, what is the source of the propulsive force? Part 3 addresses the observational paradox of the absent coma or tail. Telescopes across the globe have been meticulously observing 3 Atlas, ground-based observatories, orbital assets, and both professional and amateur astronomers have directed their instruments toward this interstellar visitor as it made its trajectory through the inner solar system. They have measured its brightness, tracked its positional changes, and searched for any indications of activity. What they have discovered is a remarkably quiescent object. The apparent magnitude of 3 Atlas has remained stable, fluctuating around 14.7 to 14.9. For context, while this is far too faint to be visible to the naked eye, it is well within the detection capabilities of moderately sized telescopes. The object's brightness has not displayed the typical variations one would anticipate from a comet becoming active as it approaches perihelion. There have been no sudden bursts of luminosity, no outbursts, and no gradual increase in brightness corresponding to rising sublimation rates. Its light curve has more closely resembled that of an asteroid than an active comet. When a comet undergoes significant outgassing, the consequences are typically evident. A coma develops, a diffuse cloud of gas and dust surrounding the nucleus. This coma can extend for thousands, even hundreds of thousands of kilometers, glowing as sunlight scatters off the dust particles and as molecules fluoresce under ultraviolet radiation. Depending on the viewing geometry, a tail may form, swept back by the solar wind and radiation pressure. Visible jets may also emerge, concentrated streams of material erupting from specific vents on the nucleus. The object's appearance undergoes changes, its brightness fluctuates, and its morphology becomes complex. 3 Atlas has exhibited none of these characteristics. High-resolution imaging has failed to resolve any significant coma. No extensive tail has been observed trailing the object. Publicly released data has shown no visible jets. The object has appeared point-like, more akin to a barren rock than a venting comet. Spectroscopic observations, where available, should have detected emission lines from volatile gases, such as water vapor, carbon monoxide, carbon dioxide, or cyanogen. These spectral lines act as unique identifiers, revealing the composition of the material sublimating from the surface. However, available reports suggest minimal or absent gas signatures, as if the object were not outgassing at all. Now, let us perform some calculations. To achieve a velocity change of 60 meters per second over a 20-day period, 3 Atlas must have been propelled by some force. If this force is attributed to outgassing, we can estimate the mass that would need to be expelled and at what velocity. The rocket equation states that delta V equals exhaust velocity multiplied by the natural logarithm of the ratio of initial mass to final mass. When dealing with a small body of uncertain mass, this calculation quickly becomes speculative, but we can make order of magnitude estimations. Let us assume the nucleus has a mass in the range of a few million kilograms, perhaps 10 million kilograms for the sake of argument. To achieve a delta phi of 60 meters per second, with gas venting at a few hundred meters per second, typical for water vapor or carbon monoxide sublimation, a significant fraction of the object's mass would need to be lost. Let us conservatively estimate this as a few percent, which translates to hundreds of thousands of kilograms of material ejected into space. Where has this material gone? Hundreds of thousands of kilograms of gas and dust should collectively form a visible coma. Dust particles are highly effective at scattering sunlight. Even with a low dust production rate, the accumulation over 20 days should result in a detectable envelope. The fact that observers are not witnessing this phenomenon presents a significant problem. It is possible that the dust-to-gas ratio is extremely low, or that 3 Atlas is expelling pure gas with minimal dust content. Gas alone is difficult to detect unless spectral emission lines are captured. However, even plumes of pure gas should be detectable through sensitive spectroscopy, and initial reports do not confirm strong gas emissions. Alternatively, the outgassing might be occurring in such minuscule quantities, spread across such a vast surface area, that the gas disperses instantaneously, preventing the formation of a dense coma. This scenario would involve invisible microjets contributing to the propulsion. This is conceivable, but it necessitates a highly specific surface structure and outgassing regime. Most comets do not operate in this manner. They tend to concentrate activity into a relatively small number of vents, producing distinct jets rather than a diffuse haze. Another possibility is that the particles being ejected are extremely small, perhaps nanoparticles or even individual molecules that do not efficiently scatter light in the visible spectrum. Smaller particles tend to scatter more strongly in the ultraviolet and infrared wavelengths. If 3 Atlas is expelling material optimized for invisibility in optical wavelengths, it could be accelerating without exhibiting visible signs of propulsion. However, this explanation introduces a very specific particle size distribution and composition, adding another layer of complexity to the natural explanation. The paradox intensifies. Acceleration implies a force, and a force implies mass ejection if we are considering rocket propulsion. Mass ejection should produce observable signatures, yet these signatures are conspicuously absent. Either the ejection is occurring in a manner we do not yet fully comprehend, or the propulsive force is not originating from mass ejection at all. If outgassing is either absent or invisible, what other mechanism could be responsible for generating the thrust? Part 3 scrutinizes natural outgassing hypotheses under duress. Let us give natural explanations their due consideration and examine each hypothesis rigorously. Science progresses by testing ideas against empirical evidence, and it is imperative that we exhaust all mundane possibilities before embracing extraordinary explanations. Hypothesis 1. Uniform vent distribution. Imagine the nucleus of 3 Atlas as a roughly spherical body adorned with numerous small vents. Solar heating penetrates the surface, causing the ice beneath each vent to sublimate and escape. If the vents are uniformly distributed and expel material at similar rates, the individual thrust vectors from each jet could combine to produce a net force that coincidentally aligns with the orbital plane. The operative word here is coincidentally. This scenario requires the nucleus's axis of rotation to align in such a way that the distribution of active vents, when averaged over time, produces no net perpendicular component. For this to be effective, the nucleus must possess a specific rotational state, with its axis of rotation being perpendicular to, or nearly perpendicular to, the orbital plane. This alignment ensures that as the nucleus spins, vents on all sides expel material symmetrically. Furthermore, the surface composition must be uniform enough that no single hemisphere dominates the outgassing process. Similarly, thermal conductivity must be consistent to prevent localized hotspots from generating more vigorous venting. While each of these conditions is plausible in isolation, their combined occurrence points to a narrow and improbable configuration. Most comets exhibit irregular surfaces, non-spherical shapes, and their axes of rotation are tilted at arbitrary angles. The probability of encountering an object that satisfies all these requirements by chance is exceedingly low. Hypothesis 2. Unusual volatile composition. It is conceivable that 3I Atlas is exceptionally rich in highly volatile ices, such as carbon monoxide, carbon dioxide, or molecular nitrogen. These substances sublime at lower temperatures and are ejected at higher velocities than water ice. High-velocity expulsion results in greater thrust for a given mass of expelled material. If the dust content is minimal, this could lead to acceleration without a prominent coma. Expelling only gas with very little dust would explain the lack of visible coma. However, this scenario still does not account for the thrust being confined to the orbital plane. Gas jets originating from a rotating body would inherently possess out-of-plane components unless the spin axis and vent geometry are perfectly aligned. Carbon monoxide readily vaporizes even when far from the sun, potentially accounting for sustained propulsion across a broad trajectory. The underlying physics is sound. Carbon monoxide has been identified in other comets and is known to generate thrust. However, this explanation still struggles with the A3 problem. Without precise alignment of the volatile distribution and the escape aperture, thrust would occur in all three dimensions. Furthermore, if carbon monoxide is driving the acceleration, we would anticipate observing its spectral signatures in emission. Observers ought to detect it. If they are not, then either the observations are insufficient to detect it, or it's not present in the necessary quantities. Hypothesis 3 proposes micro-outgassing and mass shedding. Rather than significant jets, envision the surface releasing material gradually through countless minute openings or via direct sublimation across the entire sun-facing hemisphere. While the rate of gas and dust production per unit area is low, when integrated over the entire surface and extended over weeks, it amounts to enough thrust to account for the observed acceleration. Due to the diffuse nature of this ejection, it doesn't create a concentrated coma, but rather a faint haze that current instruments cannot resolve. This scenario necessitates extremely fine-grained activity. The surface must be porous enough to permit gas to percolate through and escape uniformly, not solely from distinct vents. The thermal wave generated by solar heating must effectively penetrate the subsurface, driving sublimation beneath the surface layer. The escaping gas must carry minimal dust, or dust so fine that it remains invisible. This represents a delicate balance. Excessive dust would result in a coma. Insufficient gas would fail to produce adequate thrust. Achieving this precise equilibrium and maintaining it for 20 days demands a level of control that is seldom observed in natural processes. All three hypotheses face a shared impediment: observational constraints. The absence of a visible coma and tail is not merely a minor inconvenience for these models, it constitutes a central conflict. Every mechanism proposed to explain the thrust predicts observable consequences, and those consequences are conspicuously absent. We can introduce additional explanations, invoke specific circumstances, and refine parameters. But at some juncture, we must question whether we are distorting the explanation to fit the data or following the genuine direction indicated by the data. Thermal modeling exacerbates the issue. A small celestial body within the inner solar system is subjected to intense solar heating on its sunlit side. This energy drives sublimation. The rate of mass loss is contingent upon the volatile content, thermal conductivity, rotation period, and surface albedo. For 3I Atlas to sustain steady thrust for 20 days without discernible outgassing, all these variables must converge in a highly specific manner. The nucleus must be sufficiently small to avoid possessing substantial gravity, which would hinder efficient ejection, yet massive enough to contain adequate volatiles to sustain thrust. It must rotate rapidly enough to distribute heating evenly, but not so rapidly that centrifugal forces become dominant. Its surface properties must be such that they suppress dust entrainment while permitting gas escape. Each additional constraint progressively narrows the range of possibilities. What began as a broad category of natural phenomena, comets venting when heated, has transformed into an intricate challenge. None of these hypotheses are inherently impossible. Nature often surprises us, but they are currently under significant strain, and this strain is noteworthy. Therefore, if natural hypotheses prove inadequate, let us direct our attention to more unconventional possibilities. Part 5, Artificial Exotic Hypothesis. Light sail, propulsion, or unknown physics. We now enter the realm of speculation, and it is crucial to state that clearly from the outset. What follows are conceptual ideas, not established truths. They are scenarios that align with some of the observed data, but lack definitive substantiation. Scientific rigor demands extraordinary evidence for extraordinary claims, and we have not yet reached that point. However, given the anomaly we are confronting, these ideas cannot be dismissed without careful consideration. Hypothesis 1 posits a thin, reflective sail propelled by radiation pressure. Imagine a structure with exceptionally low mass and a large surface area, essentially a mirror tumbling through space. Sunlight strikes the surface and reflects, transferring momentum. The resulting force is small but applied consistently over days or weeks, accumulating significant effect. The critical parameter here is areal mass density, the mass per unit area. For a sail to exhibit noticeable acceleration under solar radiation, it must be exceedingly thin, perhaps only a few micrometers thick or less, and highly reflective. Let us perform some calculations. Solar radiation pressure at 1 astronomical unit from the Sun is approximately 4.5 micropascals. If 3I Atlas possesses an effective area of, for instance, a few square kilometers and a total mass of a few thousand kilograms, the acceleration could approach the observed 1 times 10 to the negative 6 astronomical units per day squared. The precise values would depend on reflectivity, orientation, and solar distance, but the order of magnitude is consistent. A sail would naturally generate thrust aligned with the sun line, predominantly radial. However, if the sail is angled relative to the sun, the thrust vector will rotate. Depending on its orientation and spin, it could generate components both radial and tangential, fitting the A1 and A2 values. The condition A3 equals 0 is satisfied if the sail's axis of rotation or orientation remains within the orbital plane, which is not implausible for a thin structure subjected to torques from radiation pressure and potentially interstellar magnetic fields. The absence of a coma is perfectly explained. A sail does not outgas, it reflects. It would appear as a faint, steady point of light, precisely as observed by astronomers. The primary challenge lies in explaining the formation of such a structure. Natural processes do not construct sails. Ice flakes or thin dust sheets might temporarily mimic sails, but maintaining coherence and orientation over weeks is difficult to justify. If 3I Atlas is indeed a sail, it is likely artificial in origin. Hypothesis 2 suggests controlled propulsion. Let us assume that 3I Atlas is equipped with a propulsion system, be it chemical, electric, nuclear, or something more esoteric. This system would operate periodically or continuously to adjust the object's trajectory. The thrust would be intentionally directed, thus accounting for the precise planar confinement of its motion. The lack of visible exhaust could imply that the propellant is something we do not readily detect, or that the exhaust velocity is so high that the plume dissipates instantaneously. For a chemical rocket, a propellant mass and an engine would be required. To achieve a delta V of 60 meters per second, with a typical exhaust velocity of a few kilometers per second, a small fraction of the total mass would be expended. A small spacecraft could conceivably carry sufficient fuel. Electric propulsion, such as ion drives, operates at much higher exhaust velocities, necessitating even less propellant. The trade-off is power. An energy source is required, whether solar panels, a nuclear battery, or some other means to power the engine. This naturally leads to the question, why? If 3I Atlas is a spacecraft, what is its mission? Why would it engage its thrusters in the midst of the solar system? Perhaps it is executing a course correction, aiming for a specific destination. It might be decelerating after an interstellar journey. The thrust could be part of a data collection or communication protocol that we do not yet comprehend. Or it could be malfunctioning, firing its thrusters unintentionally. In the absence of knowing the intent, we are left to speculate. However, the pattern of thrust appears deliberate, not random. Hypothesis 3 postulates unknown physics. What if the acceleration is generated by a mechanism that current science has not yet characterized? This could include phenomena such as dark matter drag, where 3A Atlas passes through a concentration of dark matter particles that exert a subtle force, or electromagnetic interactions, where the object carries an electric charge and interacts with the solar wind's magnetic field in an unexpected manner, or effects associated with the heliospheric boundary, where some characteristic of the heliosphere or the galactic cosmic ray wind influences motion in ways we have not yet modeled. These concepts reside at the very edge of our understanding. Dark matter remains poorly understood. We infer its existence from its gravitational effects on galaxies, but its properties and interactions are still mysterious. If dark matter can exert drag on ordinary matter under certain conditions, then objects traversing regions of higher dark matter density might experience forces. The magnitude required to explain the acceleration of 3I Atlas far exceeds current dark matter models, but those models are inherently incomplete. Electromagnetic scenarios necessitate that 3I Atlas possesses a significant electric charge or magnetic moment. Interstellar space is permeated by charged particles, including protons, electrons, and heavier ions. If an object is electrically charged, these particles will exert forces upon it. The solar wind also carries a magnetic field. Interactions between moving charges and magnetic fields generate forces. Could this account for the thrust? The issue lies in the scale of these forces. The pressure exerted by the solar wind and the magnetic forces acting on a small body are typically considerably weaker than the observed acceleration. This would require extraordinary conditions or amplification mechanisms that are currently unknown to us. Comparing these exotic hypotheses against the available data, the light sail scenario appears to be the most fitting. It provides an explanation for the planar thrust, the absence of a coma, and the consistent brightness. Controlled propulsion is almost as compelling, but it introduces unanswered questions regarding motive and origin. Unknown physics remains the most speculative possibility. While conceptually plausible, it lacks a detailed, fleshed-out mechanism. Each of these hypotheses demands further evidence. For a light sail, we would seek measurements of its albedo and reflectivity, looking for unusually high values. In the case of propulsion, we would search for directional changes and velocity adjustments consistent with deliberate maneuvers. For unknown physics, we would require theoretical advances and independent observations of similar phenomena elsewhere. The extraordinary nature of these assertions cannot be overstated. To suggest that 3I Atlas might be a sail or a spacecraft is not a casual statement. It is a hypothesis born from anomalies that resist conventional explanations. We are not claiming definitive proof. Rather, we are stating that the data makes us uncomfortable. And when data causes discomfort, one must explore all avenues, even those that sound like science fiction. Now that we have examined the anomaly and the proposed hypotheses, let us broaden our context. How does this fit into the larger picture of interstellar objects, solar system energy dynamics, and overlooked aspects? Part 6. Interstellar Objects and Comparative Behavior. Interstellar objects are transient visitors from beyond our solar system. They originated around other stars, were expelled from their home systems through gravitational interactions, and journeyed through the galaxy for millions or billions of years before entering our vicinity. Until recently, they were purely theoretical. We understood that they must exist, as probability alone dictated it. Nevertheless, we had never observed one. Then, in October of 2017, the Pan-STARRS telescope in Hawaii detected something moving at high speed, too fast to be gravitationally bound to our sun. Astronomers quickly mobilized to observe it before it departed. They named it Oumuamua, a Hawaiian term meaning scout or first distant messenger. Oumuamua was peculiar. Its trajectory was hyperbolic, confirming its interstellar origin. Its shape appeared highly elongated, possibly 10 times longer than it was wide, resembling a cigar or a pancake tumbling end over end. Its light curve exhibited periodic variations in brightness, consistent with this elongation. Furthermore, as it moved away from the Sun, it displayed non-gravitational acceleration, a slight but significant propulsion that could not be attributed to gravity alone. Some theorized outgassing, despite the absence of any visible coma or tail. Others proposed more speculative ideas, including the possibility that it was a light sail, either natural or artificial. The debate surrounding Oumuamua became quite animated. The majority of scientists favored natural explanations, arguing that unusual outgassing or an asymmetric shape could produce the observed acceleration without a visible coma. A minority, including Harvard astronomer Avi Loeb, contended that the data was more consistent with a thin, reflective object propelled by radiation pressure, possibly an artifact. This controversy underscored the extent of our ignorance regarding interstellar objects and how rapidly assumptions can be challenged when data deviates from expectations. In August of 2019, a second interstellar visitor arrived. Two came after Oumuamua. This object, named Borisov, resembled a comet, plain and simple. It developed a prominent coma and tail as it approached the Sun. Spectroscopic analysis revealed familiar volatiles, including water, carbon monoxide, and cyanogen. Its behavior aligned with what astronomers anticipate from comets, except that it originated from outside our solar system. Borisov's appearance reassured the scientific community that most interstellar objects are likely ordinary, suggesting that Oumuamua might have been an anomaly rather than the norm. Now we have Three-Eye Atlas, and it is neither like Oumuamua nor like Borisov. It shares characteristics with both, but fits into neither category. Like Oumuamua, it exhibits non-gravitational acceleration without visible outgassing, raising questions about the source of its propulsion. Like Borisov, it follows a trajectory that could be cometary, entering the inner solar system and experiencing solar heating. However, its thrust profile, characterized by precise planar confinement, sets it apart. The acceleration of Oumuamua included radial and tangential components, but also uncertainties that might have obscured out-of-plane effects. The outgassing of Borisov was clearly three-dimensional, typical of an active comet. Three-Eye Atlas occupies a middle ground, anomalous but in a distinct manner. This leads to the question, is Three-Eye Atlas simply another interstellar visitor exhibiting unusual behavior, or is it a fundamentally different type of object? If we are observing three distinct interstellar objects within less than a decade, each with unique characteristics, what does this imply about the population? Extrapolating from this minuscule sample is perilous. We are unaware of selection biases. Brighter objects are more readily detected. Highly reflective or unusually active objects might be overrepresented. We are essentially fishing with a very small net in a vast ocean of possibilities. Consider detection bias. Current surveys identify interstellar objects when they are relatively close and bright. Fainter, smaller, or less active objects evade detection. If there exists a population of low-mass, sail-like structures drifting between stars, we might only detect them when they are near perihelion and sunlight renders them visible. The same principle applies to small, inert bodies that appear only as faint points of light. The population of interstellar objects could be vastly more diverse than our three data points suggest. Envision a scenario where Three-Eye Atlas is part of a fleet, a swarm of sails or probes dispatched by some civilization long ago, intended to explore the galaxy. Most would traverse solar systems unnoticed, but occasionally one would be detected because it brightens as it approaches a star. This is highly speculative, bordering on fantastical, but it is not contradicted by the data. If intelligent civilizations exist and have mastered interstellar travel or communication, the deployment of lightweight probes is a plausible strategy. Thin sails, accelerated by starlight and carrying minimal payloads, could traverse immense distances over millennia. Alternatively, perhaps 3I Atlas is a fragment, a piece of an engineered structure that shattered eons ago. It might be discarded debris from an alien system drifting on galactic currents. Or it could be entirely natural, a type of object we have not yet characterized because we have never had the opportunity to study interstellar material up close. Perhaps comets from other stellar systems form in environments different from our own, possessing compositions or structures that lead to unusual venting regimes. Comparing the behavior across interstellar objects helps frame whether 3I Atlas represents an outlier or a turning point. If every interstellar object we discover exhibits anomalies, then anomalies become the norm, and we must adjust our expectations. If 3I Atlas stands alone, it becomes a puzzle demanding explanation. At present, with only 3 examples, we cannot definitively say, but the pattern is suggestive. Interstellar objects do not behave like native objects within our solar system. They surprise us, they challenge our assumptions, and each new discovery expands the boundaries of what we consider possible. Having examined external interstellar objects, let us now turn our attention inward to the energy environment of our own solar system and how it might influence such behavior. Part 7. The Solar System Energy Environment. Solar flares, CMEs, and geomagnetic activity. The Sun is not a static, serene ball of light. It is a turbulent nuclear furnace governed by a magnetic dynamo, and its behavior fluctuates on timescales ranging from minutes to decades. Currently, in late 2025, the Sun is intensifying its activity. Solar Cycle 25, which commenced in late 2019, is approaching its peak phase. This is the period of maximum activity when sunspots proliferate, solar flares erupt, and coronal mass ejections blast plasma into space. Solar flares are sudden releases of magnetic energy stored within the Sun's atmosphere. They manifest as brilliant flashes in extreme ultraviolet and X-ray wavelengths, expending energy equivalent to millions of hydrogen bombs. Flares are categorized by their X-ray intensity, class A, B, C, M, and X, with each successive class representing a tenfold increase in power. M-class flares are medium strength, capable of causing brief radio blackouts on Earth's sunlit side. X-class flares are the most powerful, able to trigger radiation storms and disrupt satellite electronics. Coronal mass ejections, or CMEs, are even more dramatic events. These are colossal eruptions of plasma and magnetic field from the Sun's corona, ejected into interplanetary space at speeds ranging from hundreds to thousands of kilometers per second. When a CME collides with Earth's magnetosphere, it compresses the magnetic field, inducing electric currents in the ionosphere and on the ground. Geomagnetic storms ensue, producing auroras at high latitudes, disrupting power grids, degrading GPS signals, and exposing astronauts to increased radiation levels. In 2025, observers have recorded multiple M-class and X-class flares, along with several significant CMEs. The frequency of these events is increasing as the solar cycle progresses toward its maximum, anticipated around 2025 or 2026. High-speed solar wind streams emanating from coronal holes have impacted Earth's magnetosphere, resulting in recurrent geomagnetic disturbances on an approximate 27-day cycle, which corresponds to the Sun's rotation period as observed from Earth. So, what relevance does this have to 3I Atlas? Small bodies within the solar system are not immune to the Sun's intense activity. Solar radiation and the solar wind affect them in various ways. Radiation pressure exerts a push on their surfaces, a force we have already discussed in the context of light sails. Charged particles within the solar wind can sputter atoms from exposed surfaces, eroding material atom by atom. Photoelectron emission, which occurs when ultraviolet light dislodges electrons from the surface, can electrically charge the object, creating electric fields that interact with the solar wind's magnetic field. For icy bodies, solar heating drives sublimation, the primary mechanism behind cometary activity. However, enhanced solar output during flares or CMEs could temporarily increase heating rates, triggering bursts of outgassing. Alternatively, if the object is charged, interactions with the solar wind plasma might exert forces, either augmenting or modifying the thrust generated by radiation pressure or outgassing. These mechanisms are subtle, typically producing effects far less potent than the observed acceleration of 3I Atlas. But in principle, they could contribute. The temporal coincidence is intriguing. The anomalous acceleration of 3I Atlas was detected in November 2025 during a period of heightened solar activity. Stephen Burns also pointed to this same time frame, noting a convergence of factors: the 28-day recurrence of coronal holes, peak Taurid meteor activity, a supermoon, and what he described as a significant wave of energetic disturbances affecting Earth. Is this connection real or merely coincidental? Let us quantify these forces. Solar wind pressure at 1 astronomical unit is approximately 1 to 6 nanopascals, depending on whether one is in slow or fast wind. For an object spanning a cross-sectional area equivalent to 1 square kilometer, the resulting forces would be in the order of millitons. This pales in comparison to the immense forces necessary to impart an acceleration of 3 iota Atlas's magnitude. If the celestial body possesses a mass amounting to millions of kilograms, then forces ranging from hundreds of newtons to tens of thousands of times stronger than solar wind pressure alone are required. Consequently, solar wind cannot be the primary impetus. Radiation pressure, while more potent at approximately 4.5 micropascals at 1 astronomical unit, also falls short unless the object exhibits extraordinary characteristics, such as the minimal aerial mass of a sail. During solar flares, an amplified solar output might temporarily augment radiation pressure by a few percent, which is nowhere near sufficient to account for sustained acceleration over a period of 20 days. What about electromagnetic interactions? Should 3 iota Atlas carry a substantial electrical charge, possibly accumulated through photoelectron emission or interaction with interstellar plasma prior to its solar system entry, it could engage with the Sun's magnetic field embedded within the solar wind. A charge in motion within a magnetic field experiences the Lorentz force, acting perpendicularly to both velocity and field. Depending on the charge and field intensity, this could generate forces. However, once again, the magnitudes involved are minuscule. The solar wind's magnetic field at 1 astronomical unit measures approximately 5 nanoteslas. To achieve significant force, one would necessitate enormous charges, far exceeding what photoelectron emission or conventional charging mechanisms can provide. Perhaps there exist unknown couplings, amplification mechanisms whereby solar activity instigates responses in the object's surface or interior that have thus far eluded our modeling. For instance, if 3 iota Atlas features a highly conductive surface, rapidly fluctuating magnetic fields emanating from coronal mass ejections could induce eddy currents, thereby generating magnetic moments that interact with the solar wind. This is highly speculative and would presuppose exotic material properties, but it remains conceptually feasible. A more probable connection is indirect. Solar activity influences the entire heliosphere, the expansive bubble of solar wind and magnetic field enveloping our solar system. Fluctuations in solar output alter the density, temperature, and magnetic structure of this environment. Small bodies traversing this region might encounter conditions different from those present during solar minimum. If 3 Iota Atlas is venting, enhanced solar heating or a modified ambient pressure could modulate the rate or direction of this venting. Should it be a sail, variations in radiation pressure or magnetic torque use could alter its orientation, thereby impacting its thrust. The fundamental challenge lies in the fact that none of these proposed mechanisms neatly align with the observed phenomena. The acceleration is both sustained and planar, not sporadic or reactive to solar flares. There is no discernible correlation between flare events and shifts in 3 Iota Atlas's trajectory. The link remains speculative, a tantalizing coincidence rather than a demonstrated causality. Yet, coincidences do accumulate. Stephen Burns issued a warning of a significant event, and 3 Iota Atlas began exhibiting anomalous behavior. The Sun is experiencing increased activity, and an interstellar visitor is behaving in an unexplained manner. It is possible that these occurrences are independent. Conversely, they might be interconnected. The universe operates in ways we are still endeavoring to comprehend. Forces and fields permeate space, linking distant objects through subtle interactions. When multiple systems concurrently display anomalies, it warrants an investigation into a shared underlying cause. If our Sun and heliosphere are indeed playing a role, could Earth itself be part of a larger energetic picture? This inquiry leads us into the realms of seismic activity and the big wave narrative. Part 8 delves into seismic activity, Earth's responses, and the overarching big wave narrative. Stephen Burns, while not a universally recognized name, commands considerable respect among those who monitor geophysical phenomena and space weather. His pronouncements carry significant weight. In late 2025, Burns issued a grave alert. Earth was entering a phase of intensified energetic activity, a confluence he characterized as the big wave. His reasoning is predicated on the simultaneous alignment of several factors, each possessing the potential to influence geological and atmospheric systems. Firstly, the recurrent 28-day cycle of coronal holes. Coronal holes represent regions within the Sun's atmosphere where the magnetic field extends outward into space, facilitating the escape of high-speed solar wind. These holes can persist for weeks or months, and as the Sun rotates approximately every 27 days, the same hole can repeatedly face Earth, dispatching pulses of fast wind towards us. Each such pulse compresses the magnetosphere, thereby inducing geomagnetic storms. Burns observed that in late 2025, a particularly active coronal hole was generating pronounced recurring disturbances, subjecting Earth's magnetic field to bombardment every 4 weeks. Secondly, the Taurid meteor stream. Earth intersects the Taurid stream twice annually, once in late October and early November, and again in late June and early July. This stream comprises debris originating from Comet Encke and potentially fragments from larger celestial bodies that disintegrated millennia ago. In early November 2025, Earth passed through the densest portion of this stream, encountering a greater than usual number of meteors and possibly larger particles. Some researchers have posited that meteor impacts, even minor ones, could potentially trigger atmospheric or seismic events, although definitive evidence remains scarce. Thirdly, the supermoon on November 5th, 2025. A supermoon occurs when the full moon coincides with the moon's closest orbital approach to Earth. During such events, the moon's gravitational influence on Earth intensifies, leading to increased tidal forces. Tides affect not only the oceans but also the solid Earth, resulting in measurable crustal deformations. Certain studies suggest that tidal stresses may play a role in influencing the timing of earthquakes, particularly for fault lines already nearing rupture. Fourthly, planetary alignments. Burns referenced impending alignments of Jupiter, Saturn, and other planets. configurations reputedly concentrating gravitational influences on both the Sun and Earth. While astrologers have long asserted the significance of such alignments, mainstream scientific consensus remains skeptical. The gravitational forces exerted by distant planets on Earth are exceedingly negligible when compared to the tidal forces generated by the Moon and Sun. Any discernible effect would likely be lost within the background noise. Burns integrated these factors, arguing that their simultaneous occurrence created a window of heightened energetic activity, manifesting as increased solar flares, geomagnetic storms, and, crucially, seismic events. He cited recent earthquakes, including a magnitude 6+ event in Kamchatka, Russia, another in Afghanistan, and tremors elsewhere, as evidence that Earth's crust was responding to this convergence. The scientific community's reception to such claims is, at best, equivocal. The notion that solar or geomagnetic activity might trigger earthquakes has been a subject of research for decades, yielding inconclusive results. Some studies have identified weak correlations between geomagnetic storms and shallow seismicity, particularly in volcanic regions where magma movement might be influenced by electrical currents or pressure variations. Conversely, other investigations have found no such correlation, attributing apparent patterns to statistical anomalies or publication bias. The prevailing consensus is that while external forces, such as tidal forces, can exert a minor modulating influence on earthquake timing, they do not instigate earthquakes themselves. Tectonic stress builds over years or centuries, and external triggers, at best, merely nudge already stressed faults past their breaking point. The central difficulty with the big wave narrative lies in discerning signal from noise. Earthquakes occur incessantly. Magnitude 6 events transpire hundreds of times annually on a global scale. Solar flares and geomagnetic storms are commonplace during solar maximum periods. Supermoons occur roughly every 1 to 2 years. Meteor showers are predictable occurrences. When one searches for patterns within noisy data, they are frequently discovered, even if they are merely coincidental. Humans are inherently pattern-seeking creatures, and our cognitive faculties excel at perceiving connections that may not truly exist. Nevertheless, outright dismissal of Burns's assertions would be precipitate. Scientific advancement is propelled by the examination of anomalies and the rigorous testing of hypotheses. If a genuine physical mechanism links solar activity to seismicity, its elucidation necessitates dedicated investigation, not reflexive skepticism. A subset of researchers is actively exploring how geomagnetic disturbances might influence rock resistivity. This includes investigating piezoelectric effects within rocks or alterations in pore fluid pressure within fault zones. These effects are subtle, exceedingly difficult to measure, and even more challenging to definitively prove, but their possibility cannot be entirely discounted. Now, how does this connect to 3 Iota Atlas? Burns did not explicitly correlate his big wave hypothesis with the interstellar object, yet the temporal proximity invites speculation. If Earth is indeed experiencing an energetic convergence, could analogous processes be impacting objects traversing the solar system? Could heightened solar wind or heliospheric disturbances be influencing 3 Iota Atlas's observed behavior? One perspective suggests that both phenomena might stem from a common source. It is conceivable that the solar system is currently passing through a region of interstellar space characterized by a higher density of charged particles or dust, thereby affecting both Earth's magnetosphere and smaller bodies like 3 Iota Atlas. The solar system navigates the galaxy at approximately 250 kilometers per second, and the local interstellar medium is far from uniform. We traverse clouds of gas and dust, encountering regions with varying densities and temperatures. If we have recently entered a denser region, this could amplify solar wind interactions, increase meteor influx, and potentially exert forces on smaller objects. Another avenue of consideration involves electromagnetic interactions. Earth's magnetosphere and 3-iota atlas, if electrically charged, both interact with the heliospheric magnetic field. Variations in the sun's output consequently alter the structure of that field. It is plausible that the same magnetic fluctuations inducing geomagnetic storms on Earth also affect 3-iota atlas, generating torques or forces that modify its trajectory. This hypothesis is highly speculative and would necessitate mechanisms currently beyond our understanding. A third perspective is purely observational. It is possible that the big wave is a cognitive construct, a narrative framework that aggregates disparate events due to their coincidental timing. The anomaly of 3-iota atlas, Earth's seismic activity, and solar storms might be entirely independent occurrences, and the attempt to link them could be an instance of apophenia, the perception of meaningful patterns within random data. Science mandates that we rigorously test this possibility. Burns's claims do not align with mainstream scientific consensus, and many of his specific predictions or proposed causal links lack substantial empirical support. However, the temporal clustering of these events is undeniable. Multiple systems are exhibiting activity within the same time frame. Whether this represents coincidence, a shared underlying cause, or interconnected processes remains an open question. The big wave narrative compels us to adopt a holistic perspective of the solar system as an integrated system, rather than a collection of isolated phenomena. Beyond the solar and seismic narratives, hidden data controversies and complex social dynamics within the research community also warrant examination. Let us delve into these aspects. Part 9 explores hidden angles and controversies within the scientific community. Science is ideally an objective pursuit driven by data and logic, devoid of bias and politics. In reality, the process is considerably more intricate. Scientists are human beings, possessing egos, career aspirations, funding imperatives, and intricate social dynamics that shape research priorities, publication decisions, and prevailing beliefs. The unfolding story of 3-iota atlas is not solely confined to telescopes and equations, but also plays out in conference rooms, peer review panels, and online forums where ideas clash and reputations are forged or shattered. Let us begin with data transparency, specifically concerning the non-gravitational parameters for 3-iota atlas. The values denoted as A1, A2, and A3 are derived from NASA's Jet Propulsion Laboratory Horizon system. Horizons is an openly accessible tool. Anyone can query it for orbital elements and predictions. However, the fundamental data, the astrometric observations that inform the orbital fit, originates from a multitude of sources, including professional observatories, amateur astronomers, and comprehensive sky surveys. Not all of this observational data is immediately available to the public. Some observations are proprietary, held by survey teams until their findings are published. Other data is disseminated through the Minor Planet Center, an international clearinghouse for asteroid and comet data, though its quality and completeness can vary. Independent researchers have taken the publicly available data and performed their own orbital fits, subsequently publishing their results on forums, preprint servers, and social media platforms. A portion of these analyses aligns with JPL's established solution, while others exhibit minor divergences, indicating sensitivity to the specific observational data included and the weighting applied to residuals. Orbital mechanics, while precise, is not entirely impervious to interpretation. The selection of data points to prioritize, the methodology for handling outliers, and the specific model employed for non-gravitational forces all involve subjective judgment calls. Different analysts will inevitably make different choices, leading to potentially shifting results. This presents a quandary when an individual asserts that 3-iota atlas exhibits zero out-of-plane acceleration. Are they reporting a robust finding, or is this an artifact of their particular dataset and fitting methodology? Peer review is ostensibly designed to identify and rectify such issues. However, a significant portion of the discourse surrounding 3-iota Atlas is occurring outside formal academic channels, predominantly on platforms such as Twitter, YouTube, Reddit, and various blogs. Ideas propagate with remarkable speed, while the peer review process operates at a considerably slower pace. By the time official scientific papers are published, the prevailing narrative may have already been established. Furthermore, there is the question of observed anomalies in color and reflectivity. Certain observers have reported that 3-iota Atlas appears bluer than typical comets or asteroids, exhibiting a spectrum that suggests either high reflectivity or an unusual surface composition. Blue spectral characteristics can be indicative of fresh ice, a lack of dust, or the presence of specific minerals. In the context of the light sail hypothesis, a very high albedo and a blue coloration would lend support to the notion of a reflective surface. However, accurate color measurement is inherently challenging. It is contingent upon the phase angle, the angle formed between the sun, the object, and the observer. As the phase angle fluctuates, the brightness and perceived color of reflected light undergo shifts. Observers must account for these changes, and the necessary corrections rely on models that may not be applicable to unconventional objects. Instrument calibration is another critical factor. Different telescopes, detectors, and filters all introduce systematic errors. Background sky noise, atmospheric absorption, and contamination from nearby stars further contribute to the overall uncertainty. When an individual claims that 3-iota Atlas is anomalously blue, it is pertinent to inquire, compared to what? Using which instruments? With what corrections applied? If such a claim is predicated on a limited number of data points from a single observer, it is suggestive but not conclusive. If multiple independent research teams employing disparate instruments corroborate the finding, the claim gains considerable strength. To date, the publicly available evidence remains sparse, and the scientific community maintains a cautious stance. Speculative hypotheses face significant hurdles within academic circles. Proposing that 3-iota Atlas might be an artificial construct or a light sail invariably invites skepticism and sometimes outright dismissal. The peer review system, by its very design, is inherently conservative, favoring explanations that conform to established theoretical frameworks. Papers that introduce novel physics or extraordinary claims necessitate equally extraordinary evidence, and reviewers subject them to exceptionally stringent standards. While this rigor is appropriate, it can also inadvertently stifle innovation. If every unconventional idea is rejected before the evidence can be thoroughly amassed, we risk overlooking genuine discoveries. Additionally, there is a pronounced social dimension to consider. Researchers who champion exotic explanations risk their professional reputations. Mainstream scientists may deliberately distance themselves, fearing association with fringe concepts. Funding agencies often prioritize secure investments, favoring projects that promise incremental advancements rather than paradigm-shifting breakthroughs. Career progression, tenure attainment, and the acquisition of research grants are contingent upon publishing in reputable journals, and these publications tend to favor conventional scientific work. The consequence of this dynamic is a discernible bias towards naturalistic explanations, even when the available data strains to accommodate them. Conversely, contrarian researchers who embrace speculative ideas may find themselves increasingly isolated, forming distinct communities where unconventional thinking is celebrated, but critical scrutiny might lapse. Echo chambers can emerge, wherein consensus solidifies and dissenting viewpoints are summarily dismissed. This phenomenon occurs on both sides of the divide, the mainstream dismissing the fringe and the fringe dismissing the mainstream. Social media platforms serve to amplify these dynamics. A solitary claim about 3 iota atlas, supported by preliminary data, can achieve viral dissemination long before it undergoes rigorous scientific vetting. YouTube channels, blogs, and podcasts readily seize upon anomalies, constructing narratives that captivate audiences but may not accurately reflect the scientific consensus. Mainstream scientists respond, at times dismissively, thereby exacerbating the perceived chasm between official science and independent researchers. The public observes this unfolding drama, often uncertain about whom to trust. To what extent might community bias or publication bias influence our interpretation of 3 iota atlas's anomaly? Quantifying this impact is presently impossible, yet its effects are undeniably real. If researchers unconsciously favor naturalistic explanations because they are more amenable to publication, they might not pursue exotic hypotheses with the same degree of investigative fervor. Conversely, if contrarian researchers overemphasize anomalies because they align with their pre-existing worldview, they might overlook mundane explanations that could prove to be accurate. Ideally, science engages in self-correction through replication, robust debate, and the accumulation of evidence. However, this process is inherently slow and imperfect. The crucial element in this endeavor is intellectual humility. The act of admitting our lack of knowledge, while seemingly straightforward, is often more challenging than it appears. Scientists are trained to provide definitive answers, and any degree of uncertainty can feel akin to failure. Yet, 3 iota atlas presents a genuinely perplexing enigma. The available data does not readily fit into pre-existing conceptual frameworks. Acknowledging this uncertainty, diligently exploring multiple hypotheses without premature commitment, and patiently awaiting more comprehensive data represents the most intellectually honest approach. Having examined the contextual background and the controversies, we shall now proceed to map the landscape of hypotheses and assess which hold greater promise and which are likely to prove unproductive. Part 10 presents a hypothesis matrix, mapping possibilities and their associated probabilities. Let us delineate the spectrum of potential explanations. We are confronted with several competing hypotheses aimed at elucidating the behavior of 3 iota atlas. Each hypothesis posits different requisite conditions, makes distinct predictions, and aligns with the observed evidence to varying degrees. The objective at this juncture is not to declare a definitive winner, but rather to chart the space of possibilities and identify the observations that would most decisively alter our level of confidence. Hypothesis: natural comet outgassing with uniform vents. Required conditions include a cometary nucleus possessing numerous small, evenly distributed vents, a spin axis oriented perpendicularly to the orbital plane to ensure symmetrical venting, uniform surface composition and thermal properties, and a sufficient volatile content to sustain thrust for a duration of 20 days. Current evidence supporting this hypothesis includes its hyperbolic trajectory, suggestive of an interstellar origin, and the inherent tendency of icy bodies to vent. Evidence contradicting this hypothesis comprises the absence of a visible coma or tail, stable brightness inconsistent with vigorous outgassing, and the observed zero out-of-plane acceleration, which necessitates extraordinary geometric precision. Key uncertainties revolve around the nucleus's size, shape, spin state, surface composition, and the distribution of its volatiles. Plausibility rating: moderate but with significant strain. This represents the default assumption for comets, but the lack of visible activity and the precisely planar thrust are difficult to reconcile. Hypothesis: unusual volatile composition, rich in carbon monoxide or nitrogen. Required conditions include a high concentration of supervolatiles that sublimate at low temperatures and high velocities, a low dust-to-gas ratio to minimize visible coma, and event geometry that somehow confines the thrust to the orbital plane. Supporting evidence includes the possibility that interstellar objects, having formed in distinct environments, may possess exotic compositions and supervolatiles capable of generating high thrust per unit mass. Evidence against this hypothesis includes the expectation of spectroscopic detection of carbon monoxide or carbon dioxide emissions, which have not been clearly reported, and the persistent challenge of confining thrust to the orbital plane. Key unknowns pertain to detailed spectroscopic results and the precise composition of the nucleus. Plausibility rating: moderate but confronted by observational gaps. Supervolatiles are plausible, but the absence of detected gas emissions is a concerning aspect. Hypothesis: radiation pressure acting upon a thin, low-mass, sail-like structure. Essential prerequisites include exceedingly low areal density, possibly mere grams per square meter, profound reflectivity approaching 100%, an orientation angled towards the sun, generating both outward and sideways propulsive forces, and structural integrity maintained for extended periods, spanning weeks. Corroborating observations comprise an exact alignment with the lack of a nebulous halo or trailing tail. As such, reflective surfaces do not expel gases, the planar nature of propulsion being intrinsically suited for a thin structure governed by rotational forces, a steady luminosity if the reflective properties remain constant, and the appropriate scaling of radiation pressure forces at the observed solar distances. Arguments against this explanation involve the necessity of artificial or exceptionally uncommon natural origins and the absence of direct measurements confirming high albedo or reflectivity. Nevertheless, crucial unanswered questions pertain to the measurements of albedo and reflectivity, the analysis of the phase curve, and imaging of the structure. The plausibility rating is low to moderate, but the fit is compelling. If 3II Atlas exhibits sail-like characteristics, this notion gains considerable strength. The primary obstacle is substantiating the existence of such attributes. The hypothesis posits controlled propulsion originating from an engineered craft. Necessary conditions include an onboard propulsion mechanism equipped with either propellant or an energy reservoir. Deliberate application of thrust for trajectory adjustments or deceleration, minimal detectable exhaust or exhaust too faint to register, and purposeful conduct implying sapience or pre-programmed actions. Supportive data includes precisely planar thrust, consistent with deliberate engine firings, sustained acceleration observed over 20 consecutive days, aligning with what an efficient propulsion system could achieve, and the absence of a coma, which aligns with non-chemical propulsion methods such as electric drives. The extraordinary nature of the assertion necessitates extraordinary evidence. The rationale for applying thrust mid-flight is unclear, and there are no other indicators of artificiality like radio transmissions or geometric regularity. Key uncertainties revolve around the detection of any signals or emissions, discernible alterations in trajectory indicating maneuvers, and higher resolution imaging. The plausibility rating is highly speculative, but cannot be entirely dismissed. This represents the most extraordinary hypothesis and demands the most stringent proof. The hypothesis explores exotic physics, such as dark matter interactions or electromagnetic forces. Required conditions involve traversing a region with elevated dark matter density or a concentration of charged particles, a novel interaction between the object and the interstellar or heliospheric medium, and the generation of forces on the order of 10 to the negative sixth astronomical units per day squared, sustained over a period of weeks. Supporting evidence includes the theoretical feasibility if new physical principles exist, and unexplained acceleration inviting novel mechanisms. Counterarguments include the lack of a theoretical framework predicting such effects at the observed magnitudes, the absence of independent evidence for anomalous dark matter or fields in this locale, and forces derived from known exotic mechanisms being far too weak. Crucial unknowns encompass measurements of the immediate space environment and theoretical advancements in dark matter physics. The plausibility rating is exceedingly low but conceptually open. This is the speculative frontier. Unlikely, yet not impossible. For each hypothesis, definitive observations exist that would conclusively alter the probabilities. The detection of a coma or jets would strongly favor natural gas expulsion. Measuring a very high albedo, approaching 100%, would support the sail hypothesis. Observing trajectory changes correlating with deliberate maneuvers would lend credence to the propulsion hypothesis. The identification of unusual emissions or spectral signatures might corroborate exotic physics or reveal the object's composition. High-resolution imaging revealing structured geometry would suggest artificiality. The analytical framework highlights our areas of uncertainty. We critically require superior data: spectroscopy to confirm or refute gas emissions, photometry across multiple wavelengths to constrain albedo and reflectivity, astrometry over an extended arc to refine non-gravitational parameters, and, if feasible, radar or resolved imaging to discern the nucleus itself. Each measurement refines the range of viable hypotheses. Currently, we exist in a state of productive ambiguity. Multiple hypotheses remain plausible, and none can be definitively excluded. This is an uncomfortable but honest assessment. Science flourishes in these contexts where data challenges assumptions and compels deeper consideration. The subsequent 12 months will be pivotal as more observations become available and theorists refine their models. In our concluding segment, we broaden our perspective by examining related scientific narratives from the year 2025 that may inform our understanding and expand the context. Part 11. Recent advancements in artificial intelligence and astrophysical surveying in 2025. Astronomy is inundated with data, which is a positive predicament. The forthcoming generation of sky surveys, particularly the Vera-C, Rubin Observatory's legacy, Survey of Space and Time, abbreviated as LSST, promises to image the entirety of the observable sky every few nights, generating tens of terabytes of data daily. Conventional analytical methods, which involve human image inspection or the execution of predefined algorithms, cannot keep pace. Enter artificial intelligence. In 2025, numerous research teams reported significant breakthroughs in AI-driven anomaly detection for astronomical surveys. Machine learning algorithms, especially deep neural networks, have been trained on extensive datasets of known celestial objects, including stars, galaxies, asteroids, and comets. Once proficient, these networks can meticulously examine new observations, flagging any discrepancies from established patterns. An object exhibiting unconventional motion, unusual luminosity fluctuations, or spectral characteristics that deviate from known categories is marked for further investigation. One noteworthy instance involved a collaborative effort utilizing LSST precursor data. Their algorithm identified several faint-moving objects that had been overlooked by traditional detection systems. Some of these were subsequently identified as distant trans-Neptunian objects, comprising icy bodies situated beyond Neptune's orbital path. Others were near-Earth asteroids following peculiar trajectories, and one intriguingly displayed indicators of non-gravitational acceleration analogous to that observed with 3II Atlas. The AI highlighted it due to its deviation from a purely gravitational trajectory, and subsequent analysis confirmed propulsive components that did not correspond to typical cometary gas expulsion. These methodologies operate by learning the characteristics of normality and subsequently identifying deviations in moving objects. Normality signifies adherence to Keplerian orbits, paths governed by gravitational forces. Deviations signify either measurement inaccuracies or actual physical phenomena such as venting, collisions, or, in more unusual circumstances, propulsion. The algorithms are capable of detecting these deviations in data that is too noisy or subtle for human analysts to perceive. When applied to 3II Atlas, AI tools could aid in discerning faint coma or tail features invisible to standard processing techniques. Machine learning can enhance images, extracting signals from noise by recognizing patterns in light, scattering, or the appearance of faint structures. If a whisper-thin coma surrounds 3II Atlas, an AI trained on images of active comets might detect it where human observers would not. AI also improves astrometry, the precise measurement of object positions. By analyzing thousands of reference stars and accounting for systematic errors in telescope pointing, atmospheric distortions, and detector artifacts, algorithms can refine positional accuracy to subpixel levels. Enhanced astrometry yields tighter constraints on orbital parameters and non-gravitational factors. The A2 and A3 values for 3II Atlas could be refined with improved measurements, potentially clarifying whether A3 is truly zero or merely very small. Beyond detection and measurement, AI is employed for classification. Based on an object's spectrum, light curve, or orbital path, algorithms can predict its type: asteroid, comet, trans-Neptunian object, or interstellar visitor. These classifications rely on patterns learned from extensive examples. When an object fails to fit any established category, it is flagged as anomalous. 3II Atlas would likely trigger such a classifier due to its combination of characteristics from multiple categories: interstellar origin, akin to Oumuamua, potential venting similar to comets, yet exhibiting planar thrust and lacking a coma, unlike either. The ramifications are considerable. As survey sensitivity escalates, the number of detected anomalies is projected to grow. We may discover numerous objects behaving unusually, compelling us to expand our taxonomic classifications. If several exhibit sail-like attributes, the sail hypothesis for 3II Atlas would become less extraordinary. If many display planar thrust, we would need to comprehend the natural mechanisms responsible for that pattern. Conversely, if 3II Atlas remains unique, its peculiarity is amplified. There is also the issue of false positives. AI algorithms can be misled, misinterpreting noise as signal or exhibiting overfitting to training data. Anomalies flagged by AI necessitate human verification, spectroscopic follow-up, and multi-wavelength observations. The process from initial detection to confirmation involves several stages, each presenting potential for error. However, the sheer volume of data renders AI indispensable. We cannot afford to have humans scrutinize every single image. We require intelligent filters that direct our attention to the most compelling cases. Speculation. What if AI uncovers dozens of sail-like or anomalous moving objects within archival data? These might be objects that passed through unnoticed years ago, suggesting a population of such entities, thereby altering our interpretation of 3II Atlas. Instead of an isolated, peculiar visitor, it might belong to a class, whether natural or otherwise. The existence of a class implies a formation or deployment mechanism, something responsible for producing these objects in quantity. Alternatively, if AI surveys the sky for years and identifies nothing comparable to 3II Atlas, that finding is also informative. It suggests such objects are rare, either due to their natural scarcity or because they are remnants of a sparse probe population. Rarity does not confirm artificiality, but it adds to the enigma. The subsequent challenge involves managing expectations. Increased data volume leads to more anomalies, but also to greater noise and potential misinterpretation. The interplay between human intuition and machine pattern recognition will define the next epoch of astronomical exploration. 3II Atlas is situated at the nexus of these trends, a puzzle demanding both cutting-edge tools and meticulous human judgment for its resolution. How might enhanced detection and analysis influence our understanding of 3II Atlas? Within the next 1 to 2 years, we will likely possess improved orbital solutions, more refined non-gravitational parameters, deeper imaging to search for faint features, and comparisons with newly discovered similar objects. Each piece of information brings us closer to an answer. Part 12. Advancements in Solar Physics, a major coronal mass ejection and flare event. This year, 2025. On March 19, 2025, the Sun unleashed its power. An X-3.7 class flare erupted from active region 3962, a vast expanse of sunspots near the Sun's equator. The flare reached its peak intensity at 1423 Coordinated Universal Time, inundating Earth's dayside with X-rays and extreme ultraviolet radiation. Radio operators reported widespread communication disruptions on high-frequency bands as the ionosphere absorbed the sudden energy surge. However, the flare was merely the prelude. 30 minutes later, coronagraph imagery from the Solar and Heliospheric Observatory, SOHO, revealed a colossal coronal mass ejection blasting outward from the flare's origin. The CME propelled billions of tons of magnetized plasma, expanding into a cloud hundreds of times larger than Earth. Its initial velocity was measured at over 2,000 kilometers per second, fast enough to reach Earth in less than 20 hours. When the CME impacted Earth's magnetosphere on March 20th at 1100 UT, the effect was dramatic. Solar wind pressure surged, compressing the magnetosphere and triggering a severe G4 geomagnetic storm. Auroras painted the skies as far south as the Mediterranean and across the northern United States. Power grid operators reported induced currents straining transformers. Satellite operators maneuvered spacecraft to avoid the most intense radiation, and astronauts aboard the International Space Station retreated to shielded modules. This event was not an isolated incident. It was one of several significant flares and CMEs recorded in 2025, but it exemplified the Sun's potent activity during solar maximum. These occurrences provide a natural laboratory for investigating how solar output influences the space environment and the objects within it. CMEs and flares alter conditions throughout the heliosphere. Particle fluxes escalate, bombarding planets, moons, and small bodies with protons, electrons, and heavier ions. These particles carry energy, eroding surfaces, dislodging atoms into space, and electrically charging exposed materials. For icy bodies like comets, intensified particle bombardment can modify sublimation rates or generate electric fields on their surfaces. Radiation pressure also fluctuates. While the Sun's luminosity and visible light change by less than 0.1% during flares, ultraviolet and X-ray output can increase by orders of magnitude. Objects with high albedo and those sensitive to ultraviolet wavelengths experience amplified radiation pressure during flares, potentially generating transient thrust variations. The solar wind's magnetic field, typically a few nanoteslas at 1 astronomical unit, can surge tenfold during CME passages. Rapidly shifting magnetic fields induce electrical currents in conductive materials. If 3II Atlas possesses metallic components or conductive ice, these currents could generate magnetic fields that interact with the solar wind, producing forces or torques. Could the March 19th event or similar occurrences have initiated or amplified 3II Atlas's anomalous acceleration? The timing is not perfectly aligned. 3II Atlas's non-gravitational acceleration was detected in November, months after the March event, but solar activity remained elevated throughout 2025, with multiple M and X-class flares and recurring CMEs. If a connection exists, it would likely stem from sustained environmental changes rather than a single incident. One possibility involves cumulative effects. Repeated CMEs and high-speed solar wind streams erode surfaces over time. If 3II Atlas entered the inner solar system during a period of heightened activity, its surface might have undergone modification, exposing fresh volatile compounds or altering its reflective characteristics. This could, in turn, affect its response to solar heating or radiation pressure. Another perspective involves plasma interactions. The solar wind is a plasma, a collection of charged particles. Objects traversing plasma can develop bow shocks, regions where the plasma flow is disrupted. If 3II Atlas is electrically charged, its interaction with the plasma could be intricate, potentially generating forces. During CME passages, plasma density and velocity spike, intensifying these interactions. However, the forces involved are typically small, significantly weaker than the observed acceleration. Theoretical investigations in 2025 have explored the impact of extreme solar events on small bodies. One study modeled dust ejection from asteroids during CME impacts, concluding that electrostatic forces can lift dust particles from the surface, forming transient clouds. If 3II Atlas is shedding dust electrostatically rather than through sublimation, this might account for the absence of a visible coma. The dust disperses too rapidly to form a concentrated cloud. Nevertheless, this mechanism produces intermittent, not continuous, thrust. The most probable conclusion is that advancements in solar physics expand our comprehension of the environmental parameters influencing small body behavior, but do not fully elucidate 3II Atlas. Solar events modify the surroundings, but the object's reaction depends on its inherent properties: composition, structure, electrical charge, and reflectivity. Without knowledge of these characteristics, we cannot definitively ascertain the significance of solar activity. Speculative scenario: what if 3II Atlas traversed a transient enhancement in the solar wind, a dense, slow-moving structure ejected from the sun, and the interaction generated drag or thrust that persisted for days? Solar wind structures can extend for tens of millions of kilometers, and an object moving through one might experience sustained forces. This is a far-fetched idea. The forces are weak, but in conjunction with other mechanisms, they might contribute. Solar physics demonstrates that the heliosphere is a dynamic, not static, environment. Conditions vary with spatial location, temporal progression, and the level of solar activity. 3II Atlas's journey through this environment is shaped by these variations. Understanding solar influences helps define the realm of possibilities, even if it does not fully resolve the mystery. Part 13, New Findings in Small Body Physics, Sample Return or Comet Mission Results, September 2025. In September of 2025, the Japan Aerospace Exploration Agency, JAXA, announced a remarkable new set of findings from the ongoing extended analysis of samples returned by its Hayabusa 2 mission to asteroid Ryugu. While the spacecraft had delivered its precious cargo to Earth in late 2020, detailed laboratory investigations of the microscopic grains have continued for years, and the new results, published in Nature Astronomy, may have fundamentally altered scientists' perspectives on outgassing, surface evolution, and non-gravitational acceleration in small celestial bodies. At first examination, Ryugu appeared well understood. It was characterized as a dark, carbonaceous near-Earth asteroid, highly porous and loosely aggregated, more of a rubble pile than a solid mass. However, the 2025 findings unveiled deeper insights. Ryugu's constituent grains are riddled with microscopic fractures, nanovoids, and channels, forming an internal structure resembling a sponge. Embedded within this structure are hydrated minerals and trace organic compounds, indicative of past aqueous alteration. What surprised scientists, however, was the behavior of these grains under vacuum and heat. When subjected to simulated sunlight in laboratory conditions, the samples released gases persistently, even though they appeared dry. This process is not characterized by explosive venting, as depicted in the classic imagery of cometary jets erupting from a nucleus. Instead, it is diffusive outgassing. Trapped volatiles, including water molecules, carbon dioxide, nitrogen, and other trace gases, migrate slowly outward through a complex network of pores. The gas release is gentle, uniform, and sustained, generating a continuous, low-level propulsive force. Researchers estimated that on a body the size of an asteroid, this mechanism could produce non-gravitational acceleration detectable over days or weeks, yet without forming a visible coma or tail. This is where 3II Atlas becomes relevant. If the interstellar object 3II Atlas possesses a similarly porous and volatile-rich structure, this mechanism could offer a natural explanation for its enigmatic, sustained in-plane acceleration, the phenomenon reported by NASA's JPL Horizon system in November 2025. Unlike typical comets, which vent through localized jets, producing visible plumes and asymmetric thrust, a diffusively venting body would exert thrust uniformly across its surface, resulting in a subtle, smooth acceleration, precisely as observed. This could also account for the absence of a detectable coma or tail. The gases might be escaping too uniformly and too faintly to scatter light or carry dust in quantities that can be detected. If the predominant volatiles are weak emitters, such as nitrogen, argon, or carbon monoxide, then even the most sensitive spectroscopic surveys might fail to detect them. In essence, 3II Atlas might be venting invisibly. Nevertheless, this elegant theory still faces challenges. The A3 value of 0 in the JPL orbital solution, indicating no out-of-plane acceleration, remains a persistent issue. Even with diffuse outgassing, a rotating body should exhibit variations in thrust direction unless its spin axis fortuitously aligns with its orbital plane, a highly improbable coincidence. Therefore, while the Hayabusa 2 findings broaden the spectrum of possible natural behaviors, they do not conclusively resolve the mystery. The geometry of the situation remains significant, and thus far the numerical data does not align perfectly. Despite these reservations, the implications of Ryugu's gentle outgassing are profound. It suggests that the distinction between asteroids and comets is less defined than previously understood. A celestial body can appear inert and rock-like, yet still exhibit subliminal activity when exposed to solar heating. Over extended periods, such subtle outflows could even alter an asteroid's trajectory, or, within an interstellar context, mimic controlled motion. Providing further context, the European Space Agency's Comet interceptor mission, slated for deployment in the latter half of the 2020s, disseminated a collection of preliminary papers in the year 2025. These documents outlined its strategic approaches for examining nascent long-period or interstellar visitors. Within this series, a simulated investigation delved into the phenomenon of microjets, narrow, sporadic bursts of gas and dust. These are too faint to be detected from Earth, but possess the potential to generate discernible propulsive force. According to these simulations, microjets could impart net accelerations in the range of 1 millionth to 7 millionths of an astronomical unit per day squared, a magnitude consistent with observations of 3I Atlas. Critically, these jets could activate intermittently, influenced by solar radiation and surface temperature. Nevertheless, their average effect could manifest as a nearly consistent acceleration, provided the object's rotational and orbital configuration aligned favorably. From Earth's perspective, this would appear precisely as a smooth, in-plane propulsion, the very signature that currently perplexes astronomers. The Comet interceptor studies also highlighted that the texture of a surface, encompassing the distribution of fissures, craters, and granular inclines, can profoundly impact how solar energy is absorbed and re-emitted. A rugged, porous surface can intensify localized heating and sublimation, even at considerable distances from the Sun. When considered alongside the insights gained from Ryugu's porous composition, the emerging picture depicts small celestial bodies as dynamic, evolving surfaces continuously sculpted by subtle physical forces imperceptible at telescope resolution. Concurrently, complementary findings from NASA's OSIRIS-REx mission, which successfully retrieved samples from asteroid Bennu in the year 2023, reinforced this same perspective. Analyses published in 2024 and 2025 revealed that Bennu's regolith is similarly delicate and porous, possessing a mechanical integrity lower than anticipated, more akin to compacted dust than solid rock. Such a structure could facilitate the outward diffusion of deep-seated volatiles more readily than previously hypothesized. OSIRIS-REx also documented instances of particle ejection during its close proximity operations around Bennu, where minute grains spontaneously detached from the surface without any apparent vents. Taken together, the data from Hayabusa 2 and OSIRIS-REx have collectively painted a revised portrait. Small bodies are not merely inert masses of rock, but intricate, semi-active aggregates capable of producing measurable accelerations without overt visual indications. For 3 Atlas, this offers a compelling parallel, though not definitive proof, suggesting its behavior might be part of a spectrum of natural processes that we are only beginning to quantify. Naturally, speculation abounds. Could the microstructure of an interstellar object exhibit even more radical variations? Having traversed interstellar space for millennia, subjected to cosmic ray bombardment, and frozen far beyond the heliopause, its surface might have developed unique reactivity. As such a body re-enters the solar system, abrupt solar warming could trigger trapped volatiles in unforeseen ways, much like activating a long-dormant power source. Some researchers have proposed that interstellar material could even contain unusual ices or amorphous carbon matrices unfamiliar in typical comets, which might sublimate differently under solar radiation. Others extend this line of thought further. Within more speculative circles, the uniform acceleration and directional steadiness of 3 Atlas have reignited comparisons to Oumuamua, whose own non-gravitational acceleration in the year 2017 sparked discussions regarding light sails, artificial probes, and technologically engineered materials. If 3 Atlas exhibits similar undetectable, constant propulsion but via a different structural mechanism, porous outgassing rather than reflective pressure, it might indicate that multiple natural pathways can mimic propulsion. Or, as some surmise, it could point to a deeper, as yet uncomprehended pattern among interstellar visitors. The implication is both humbling and exhilarating. The more precisely we measure, the more anomalies come to light. Hayabusa 2 and OSIRIS-REx have demonstrated that microscopic surface features can influence macroscopic motion. ESA's Comet interceptor is designed to capture one of these bodies in action, potentially an interstellar visitor, to directly observe the invisible physics at play. When this occurs, it could reveal whether 3 Atlas's behavior represents the next evolutionary stage for natural small bodies, or something that defies even that categorization. In essence, the key to unraveling the mystery of a billion-ton object drifting among the stars might lie within a few milligrams of dust contained within a laboratory in Japan. Part 14. Frontier Physics, Dark Matter, Modified Gravity, and Hypotheses Regarding Spacecraft-like Objects. We have examined natural mechanisms and even contemplated the possibility of artificial constructs. However, another category of explanation resides at the forefront of theoretical physics. Hypotheses that involve forces or interactions we are only beginning to comprehend or have yet to definitively confirm. These concepts necessitate venturing beyond the established confines of conventional science to inquire whether the universe harbors phenomena that our current models entirely overlook. Dark matter, modified gravity, exotic particles, and heliospheric boundary effects each represent a frontier where observational data is outpacing theoretical understanding and where observed anomalies might serve as indicators of new physics. Dark matter stands as one of the most profound unsolved enigmas in contemporary cosmology. Its existence is inferred from the observation that galaxies rotate at speeds inexplicable by visible matter alone. Galaxy clusters remain cohesive despite insufficient luminous mass. Gravitational lensing reveals mass distribution where no visible matter is present. The evidence overwhelmingly suggests that approximately 85% of the universe's matter is dark, interacting primarily through gravitational forces and potentially through other undetected forces. But its fundamental nature remains elusive. Theoretical candidates include weakly interacting massive particles, axions, sterile neutrinos, primordial black holes, and more speculative options. Despite decades of dedicated research, direct detection of dark matter particles has not been achieved, leaving their behavior at small scales and their potential subtle interactions with ordinary matter beyond gravity unknown. Now we venture into a speculative leap. What if dark matter is not uniformly distributed on the scale of the solar system? What if it exists in localized clumps, streams, or concentrations that celestial objects traverse? The Milky Way galaxy is theorized to contain dark matter halos and substructures, remnants of smaller galaxies that merged with our own in the distant past. Some models predict the existence of dark matter streams threading through the galaxy, coherent flows of particles moving in unison. If the solar system is passing through such a stream, or if 3I Atlas entered the solar system on a trajectory that intersected a dark matter concentration, could this exert a retarding force? The underlying physics becomes ambiguous at this juncture, as our understanding of how dark matter couples with ordinary matter beyond gravity is limited. If dark matter particles scatter off atoms or nuclei, even with extreme rarity, they could transfer momentum. An object moving through a dark matter cloud would experience drag, a force opposing its motion. However, the cross-section for such interactions, if they occur at all, is constrained by experimental data to be exceptionally small. Dark matter is termed dark precisely because it does not interact strongly. To generate a force equivalent to 1/1,000,000th of an astronomical unit per day squared on an object with a mass in the millions of kilograms would necessitate dark matter densities far exceeding anything predicted or observed in our galactic vicinity. To quantify this, the estimated local dark matter density near the Sun is approximately 0.3 gigaelectron volts per cubic centimeter, a density roughly 100,000 times lower than that of interstellar gas. If dark matter particles possess masses around 100 gigaelectron volts and scatter off nuclei with cross-sections approaching current experimental limits, the drag force on a kilometer-sized object would be utterly negligible, orders of magnitude below what is required to explain 3I Atlas. To achieve meaningful drag, one would require either substantially higher dark matter densities, significantly larger scattering cross-sections, or some amplification mechanism. None of these conditions are supported by current empirical evidence. However, what if dark matter interacts via a fifth fundamental force, distinct from gravity and the interactions described by the Standard Model? Certain theories propose that dark matter couples to ordinary matter through novel bosons or via interaction portals involving Higgs-like fields. If such a force exists and operates over distances comparable to astronomical units, objects traversing dark matter fields could experience accelerations. The primary challenge lies in the fact that these forces must be exceedingly weak to have evaded detection in laboratory experiments and in observations of solar system dynamics to date, yet simultaneously strong enough to influence 3 Atlas. Navigating this fine balance demands highly specific and contrived parameters. Another frontier hypothesis involves modified Newtonian dynamics, or MOND, and its relativistic extensions, such as modified gravity theories. MOND was initially proposed as an explanation for galactic rotation curves without invoking dark matter, by postulating that gravity behaves differently at extremely low accelerations. Within the MOND framework, when accelerations fall below a critical threshold of approximately 10 to the negative 10th meters per second squared, gravitational attraction becomes stronger than predicted by Newton's inverse square law. This threshold is close to the accelerations experienced at the outer edges of galaxies, which is why MOND effectively explains phenomena at those scales. Could MOND or related theories be applicable to 3 Atlas? The object's acceleration is approximately 1/millionth of an astronomical unit per day squared, which converts to roughly 10 to the negative 8th meters per second squared. This value is higher than the MOND threshold, but it falls within a regime where modified gravity effects might still be relevant, depending on the specific theoretical formulation. If gravity transitions smoothly rather than abruptly at the threshold, residual corrections could potentially produce anomalous accelerations. The fundamental issue is that MOND and its variations are designed to account for phenomena observed at galactic scales, not within individual solar systems. Within our solar system, Newtonian gravity complemented by general relativity provides exceptionally accurate predictions. Spacecraft trajectories, planetary orbits, and even the precession of Mercury's orbit all align with theoretical predictions to an extraordinary degree of precision. Invoking modified gravity to explain the motion of a single small body necessitates that this modification is somehow sensitive to the body's specific characteristics, its composition, electric charge, or origin, in a way that does not affect planets or conventional asteroids. This represents a significant demand and would constitute a substantial departure from the principle of universality of gravity that underpins our current understanding of physics. A related concept involves the boundary of the heliosphere and interactions occurring at the edge of the sun's influence. The heliosphere is essentially a bubble of solar wind and magnetic fields that envelops the solar system, extending approximately 100 astronomical units in the direction of the sun's galactic motion, and less in other directions. At the heliopause, the boundary where the outward pressure of the solar wind balances the inward pressure of the interstellar medium, conditions change abruptly. The density of charged particles shifts, magnetic field orientations reverse, and the environment transitions from one dominated by solar activity to one governed by galactic influences. 3I Atlas, being an interstellar object, presumably traversed the heliopause. Could crossing this boundary have imparted an electric charge, a magnetic moment, or some other property that now causes it to interact anomalously with the solar wind or the heliospheric magnetic field? In principle, this is plausible. The heliopause is a complex region characterized by particle acceleration, magnetic field reconnections, and the formation of shock waves. Objects transiting this zone might undergo alterations, acquiring surface charges or embedding magnetic fields. However, even if 3I Atlas became electrically charged or magnetized at the heliopause, the forces it would experience from the solar wind within the inner solar system depend on the magnitude of that charge or magnetization and on the prevailing local solar wind conditions. As previously discussed, typical solar wind forces are far too weak to account for the observed acceleration. This would necessitate extreme charging, potentially with the object acting as a colossal capacitor, or unusual magnetic properties that establish a strong coupling with the interplanetary magnetic field. There is no empirical evidence to support such properties, and postulating them without independent corroboration appears to be an unsubstantiated embellishment. Galactic cosmic rays, which are high-energy particles originating from supernovae and other energetic cosmic events, permeate the heliosphere. Their flux varies in accordance with solar activity. The solar wind moderates their density, reducing their concentration closer to the sun. Could cosmic rays interact with 3I Atlas in a manner that generates thrust? If the object possesses superconducting materials or possesses unconventional electromagnetic properties, it might channel or reflect cosmic rays in an asymmetrical fashion, thereby generating a net force. This is a highly speculative notion, requiring materials and structures that have never been observed in nature. Furthermore, there is the concept of an interstellar wind composed of exotic particles. What if there exists a population of particles yet to be detected? Not dark matter, but something distinct, perhaps sterile neutrinos with subtly different characteristics or hypothetical particles arising from extensions of the Standard Model that stream through the galaxy. If these particles interact with matter more strongly than dark matter, but are sufficiently rare to have evaded detection, an object traversing a stream of them could experience either drag or thrust. The parameters involved would need to be precisely fine-tuned, common enough to affect 3I Atlas over a period of 20 days, rare enough not to be evident in other observations, and interacting with just sufficient strength to produce the measured acceleration without any other discernible consequences. All these frontier physics hypotheses share a common characteristic. They depend on the existence of new, unconfirmed physics to be viable. They are not extensions of well-established theories, but rather speculative additions to our current understanding of the cosmos. This does not inherently render them incorrect. Scientific progress is driven by the proposal and testing of novel ideas. However, it places them in a distinct category from natural or even artificial explanations. Natural explanations rely on known physical principles applied in innovative ways. Artificial explanations invoke known engineering principles scaled up or utilized by external agents. Frontier physics explanations posit unknown mechanisms, which inherently makes them more challenging to test and more susceptible to manipulation to fit observed anomalies. That said, historical precedent demonstrates that anomalies can indeed point toward new physics. The anomalous precession of Mercury's orbit, which Newtonian gravity could not fully reconcile, ultimately led to the development of general relativity. The rotation curves of galaxies presented an anomaly that spurred the hypothesis of dark matter. The accelerating expansion of the universe was an anomaly that introduced the concept of dark energy. Not every anomaly signifies a breakthrough. Most are eventually attributed to measurement errors or misunderstandings of known effects. However, some anomalies are genuine. The crucial question is how to differentiate between them. For 3 Atlas, the pathway to validating a frontier physics hypothesis would necessitate multiple converging lines of evidence. Firstly, the anomaly must persist and strengthen with improved data, thereby ruling out observational artifacts. Secondly, the proposed mechanism must yield testable predictions beyond merely explaining the behavior of 3I Atlas. For instance, if dark matter drag is indeed a real phenomenon, other small bodies in comparable regions should exhibit analogous effects. If heliospheric interactions are responsible for generating the thrust, correlations with solar wind conditions should be observable, or the effect should be replicable in laboratory simulations. Thirdly, independent experimental investigations or observations must corroborate the underlying physics, such as detecting dark matter interactions, measuring modified gravity at relevant scales, or discovering the hypothesized exotic particles. None of these crucial steps have yet been undertaken for 3I Atlas. The frontier physics explanations currently remain conceptual frameworks for contemplating possibilities rather than established theoretical models. While valuable as intellectual exercises that prompt us to question assumptions and explore the boundaries of knowledge, they should not be mistaken for definitive answers. There is also a psychological dimension to frontier physics explanations. Their appeal stems from their exotic nature and transformative potential. The prospect of 3 Atlas serving as evidence for new physics is undeniably exciting, representing a discovery that could fundamentally reshape our understanding of the universe. The temptation exists to prematurely embrace such explanations, to favor the revolutionary over the mundane. Science mandates that we resist this inclination, diligently exhausting conventional explanations first and demanding rigorous proof before accepting radical new ideas. Nevertheless, we must also avoid being so conservative that we disregard genuine signals of new physics. Striking this balance is a delicate task. In the case of 3 Atlas, the observational data is anomalous enough to warrant thorough investigation, including the exploration of unconventional concepts. However, it is not yet sufficiently compelling to overturn established physical laws or to justify the construction of new theories centered around a single object. Perhaps the most accurate stance at present is to acknowledge that frontier physics hypotheses for 3 Atlas currently carry a very low probability of being correct. However, they effectively highlight the limitations of our current knowledge and underscore the possibility that the universe holds unforeseen surprises. If 3 Atlas's behavior remains unexplained after an exhaustive examination of natural and artificial mechanisms, and if similar anomalies begin to accrue across other celestial objects or systems, then revisiting these frontier ideas would become considerably more justified. Until such a point, they serve as potent reminders that scientific inquiry is an ongoing process, that the vast expanse of the unknown continues to far outweigh our accumulated knowledge, and that maintaining intellectual openness is as vital as exercising skepticism. The dynamic interplay between established physical principles and speculative frontier theories defines the scientific method. We build upon a foundation of robust understanding while remaining vigilant for subtle imperfections, anomalies that do not conform, and signs that might indicate something more profound. 3 Atlas represents such an anomaly. Whether it ultimately undermines our foundational understanding or proves to be a peculiar yet ultimately natural phenomenon remains to be determined. However, the act of posing these questions, of considering even the less probable possibilities, and of designing observational strategies to test them is precisely how science progresses. In our concluding section, we will synthesize these findings to offer a forward-looking perspective, outlining what to monitor in the upcoming 12 months and what implications these developments hold. Part 15, Synthesis and Forward Look. What to observe in the next 12 months. We have embarked on an extensive journey together, commencing with the initial anomaly presented by 3 Atlas's unexplained propulsion, proceeding through natural hypotheses that strain under scrutiny, and venturing into exotic possibilities of artificial propulsion systems and frontier physics at the very edges of our comprehension. We have contextualized this object within the framework of other interstellar visitors, examined the energetic environment of our solar system, and explored the social dynamics that influence scientific interpretation of anomalies. Now it is time to step back, take stock of our current understanding, identify the areas where knowledge is lacking, and anticipate the observations and discoveries that may resolve this enigma or deepen its complexity. Let us begin by outlining what we know with a reasonable degree of certainty. 3 Atlas is traversing the inner solar system on a hyperbolic trajectory consistent with an interstellar origin. It is exhibiting non-gravitational acceleration characterized by radial and tangential propulsive components, designated as A1 and A2, respectively, while demonstrating a zero measurable out-of-plane acceleration, A3 equals 0. This acceleration has been sustained for approximately 20 days, resulting in a velocity alteration of about 60 meters per second. Observationally, the object presents as a faint point of light, with a magnitude ranging between 14.7 and 14.9. It displays no significant variations in brightness and no clearly discernible coma, tail, or jets in publicly available imagery. Spectroscopic observations, where available, have not reported strong emission lines indicative of typical cometary volatiles, such as water vapor or carbon monoxide. Now, let us enumerate the aspects that remain unknown, a list that is both longer and more consequential. We do not know the precise size or shape of 3 Atlas's nucleus due to the absence of resolved imaging. Our estimations are based solely on its brightness and an assumed albedo, and the albedo itself is unknown. A dark object will appear faint for its actual size, while a bright, reflective object may appear faint because it is small. The potential dimensions of this object span a vast spectrum. Its mass remains unknown. Without knowing its size and density, its mass is entirely unconstrained. And this mass is absolutely crucial for determining the forces required to achieve the observed acceleration. We lack knowledge of its surface composition, including which minerals coat the nucleus, what volatile substances it contains, or how its reflectivity varies across different light wavelengths. We are also unaware of its rotational state, how rapidly it spins, the orientation of its axis of rotation, or whether its movement is stable and consistent or chaotic tumbling. Its thermal characteristics are also unknown, specifically how effectively it absorbs and dissipates heat, or how heat propagates through its internal structure. Furthermore, we have no insight into its origins, such as which stellar system it originated from, how long it has been traversing the galaxy, or the environment in which it initially formed. Each of these unanswered questions hinders our ability to differentiate between competing hypotheses. A diminutive, highly reflective body would perfectly align with the solar sail hypothesis, but would be an implausible candidate for a naturally occurring comet. A substantial porous object rich in volatiles might better explain natural outgassing, yet it struggles to account for the absence of a visible coma. A dense, rocky entity containing embedded volatiles could potentially explain subtle venting without being readily apparent. But this raises questions about its capacity to retain ice. An object possessing an unusual composition, particularly one abundant in carbon monoxide or nitrogen, might produce high-velocity gas emissions that escape detection, though it should still exhibit spectral indicators. Until these characteristics are better understood, our theoretical models are built on uncertain foundations. Therefore, what should we focus on observing in the upcoming 12 months? First and foremost, orbital trajectory updates. NASA's Jet Propulsion Laboratory's Horizon system continually refines orbital solutions as new astronomical observations are acquired. Any alteration in 3I Atlas's trajectory, any shift in its non-gravitational parameters, or any change from 0 to a non-zero value for A3 would be highly informative. A transition from planar to three-dimensional thrust would suggest a change in outgassing geometry, possibly due to different regions of the nucleus rotating into sunlight. Persistent planar thrust would bolster the argument for either precise geometric alignment or active directional control. Trajectory modifications resembling deliberate maneuvers, such as sudden velocity adjustments that correspond to specific objectives, would constitute extraordinary evidence supporting a propulsion system. Second, concerted telescope observation campaigns. Several major observatories have already scheduled observation time or could propose observations of 3 Atlas. The James Webb Space Telescope, with its exceptional infrared sensitivity, could detect thermal radiation emanating from the nucleus, thus constraining its size and temperature. It could also identify faint molecular emissions in the infrared that are imperceptible to ground-based telescopes. These would include gases like carbon monoxide, methane, or carbon dioxide, which sublimate readily but emit weakly at visible wavelengths. Large ground-based telescopes equipped with adaptive optics, such as the Keck telescopes in Hawaii or the Very Large Telescope in Chile, could attempt resolved imaging to discern the nucleus as something more than a point source. This would involve searching for evidence of a coma structure, jets, or elongation that might suggest its shape or activity. Spectroscopic analysis across ultraviolet, visible, and infrared wavelengths would contribute to a comprehensive understanding of 3 Atlas's composition and whether it is exhibiting venting activity. Third, photometric monitoring. Continuous measurements of its brightness over several months can reveal its rotation period through variations in its light curve. This would also help constrain its albedo by comparing its brightness at different phase angles and detect any fluctuations in its activity level. If 3i Atlas experiences a sudden increase in brightness, this could indicate a new outburst, possibly delayed venting triggered by subsurface warming or fragmentation. Conversely, if it fades more rapidly than anticipated, this might suggest a change in its reflectivity or orientation, which would be pertinent for evaluating the solar sail hypothesis. Fourth, radar observations. Planetary radar systems, such as the Goldstone Solar System radar in California or the Arecibo telescope prior to its collapse, have been utilized to observe asteroids and comets, providing direct measurements of their size, shape, spin, and surface texture. Goldstone remains operational and could potentially detect 3 Atlas if it approaches sufficiently closely and is large enough to produce a detectable signal. Radar observations would definitively constrain its size and reveal whether the object is elongated, spherical, or irregularly shaped, information that is critical for distinguishing between hypotheses. Fifth, AI-driven surveys and archival data analysis. As elaborated in Part 2, machine learning algorithms are meticulously examining archived data from sky surveys to identify anomalies. It is conceivable that 3i Atlas was imaged months or even years ago during its inbound journey, but these observations were either not recognized or not flagged. The recovery of pre-discovery images would extend the observational timeline, leading to improved orbital calculations and potentially indicating whether the non-gravitational acceleration began gradually or abruptly. AI might also facilitate the discovery of similar objects in ongoing surveys, and the existence of a population of such objects would fundamentally alter our perspective. If 3i Atlas is merely one among many, we are likely observing a class phenomenon rather than an isolated event. Sixth, solar and heliospheric monitoring. Tracking solar activity, including flares, coronal mass ejections, solar wind conditions, and their temporal relationship to any changes in 3 Atlas's behavior, could unveil correlations. If the object's acceleration intensifies or diminishes in response to solar events, this would suggest an environmental influence. Conversely, if its behavior is independent of solar variations, this would point towards intrinsic mechanisms, either venting or propulsion, driven by internal processes. Seventh, theoretical advancements. Papers are undoubtedly being authored at this very moment, modeling various scenarios and testing whether specific compositions or structures can replicate the observed phenomena. Publications in esteemed journals such as Nature, Science, the Astrophysical Journal, or Icarus will present competing interpretations, which the scientific community will then rigorously debate. A consensus may emerge, or the discussion might remain unresolved, but the theoretical work will undoubtedly refine our understanding of what is physically plausible and what is not. Eighth, mission proposals. While unlikely, it is not impossible that space agencies might expedite the development of a mission to intercept or conduct closer observations of 3 Atlas. Interstellar objects travel at high velocities and are consequently difficult to intercept. However, if 3 Atlas is deemed sufficiently significant, a flyby mission utilizing existing spacecraft or a rapid response probe could be proposed. The European Space Agency's Comet interceptor mission is designed for such opportunities, although its launch is not anticipated until the late 2020s. Nevertheless, the prospect of close-up observation, even from a small CubeSat, would provide conclusive answers. Now, let us consider potential scenarios for how this situation might unfold over the next year. Scenario A, confirmation of a natural explanation. High-resolution imaging or spectroscopy reveals a faint coma or jets that were previously undetectable due to their low intensity. These jets are found to be aligned in such a way, dictated by the nucleus's rotation and shape, that they produce a net thrust confined within the orbital plane. The object's composition is determined to be rich in highly volatile substances like carbon monoxide, which would account for the high-velocity venting and minimal dust production. A detailed model incorporating all these factors accurately reproduces the observed acceleration, thereby resolving the mystery. 3 Atlas would then be recognized as a remarkable instance of an unusual but fundamentally natural interstellar comet, and we would learn that our preconceptions about cometary behavior were too limited. The object would enrich our understanding but not revolutionize it. Scenario B, growing credibility for an exotic explanation. Photometric observations across multiple wavelengths indicate an unusually high albedo, approaching 90 to 100%, far exceeding that of any known natural comet. Analysis of the phase curve suggests that 3I Atlas reflects light like a smooth, flat surface, rather than a rough, irregular rock. Thermal measurements indicate a very low mass, implying an extremely low density inconsistent with solid ice or rock. Collectively, these findings point towards a thin, lightweight structure, akin to a sail. The scientific community would then debate whether such a structure could form naturally, perhaps as a frozen sheet of volatiles in interstellar space, or whether it is artificial. No immediate consensus would be reached, but the solar sail hypothesis would emerge as the leading explanation, initiating a new phase in the study of interstellar objects and raising profound questions about whether we are observing technology, either human-made or originating from another civilization, adrift among the stars. Scenario C, absence of a decisive resolution. Additional observations would refine our knowledge, but would not definitively support any single hypothesis. The coma would remain absent or only barely detectable. Albedo measurements would be inconclusive. The non-gravitational parameters would continue to be puzzling. 3I Atlas would fade as it recedes from the inner solar system, becoming too faint for detailed study. The object would remain an enigma, categorized as an anomaly that could not be explained with the available data. Years later, with the advent of superior instruments or the discovery of more examples, scientists might revisit 3 Atlas. However, in the short term, it would represent an unsolved puzzle, a frustrating reminder of the limitations of current observational capabilities. Each scenario carries distinct implications. Scenario A, the natural explanation, would be profoundly satisfying in many respects, demonstrating that nature is more varied and extraordinary than we had previously realized, while affirming the fundamental soundness of our physical models. It would encourage observers to scrutinize future interstellar objects more closely, to avoid assuming that comets necessarily exhibit visible venting, and to anticipate the unexpected. Scenario B, the exotic resolution, would be truly transformative. If 3I Atlas is indeed a sail, whether natural or artificial, it would compel us to broaden our conception of what exists in the galaxy, how matter organizes itself on vast scales, and potentially whether intelligence is a rare or common phenomenon. The implications would extend into the realms of philosophy, astrobiology, and technology. Scenario C, the unresolved mystery, is the least satisfying but perhaps the most realistic. Scientific progress often proceeds at a deliberate pace, constrained by resources, technological limitations, and the inherent difficulty of observing faint, distant objects. Not all questions are answered promptly, and some remain open for decades. Beyond the immediate resolution of this case, 3 Atlas prompts broader inquiries into how we detect and interpret anomalies. This object was recognized because our monitoring systems are sufficiently advanced to detect minute deviations from gravitational orbits, and because the astronomical community is attentive to interstellar visitors. However, how many anomalies do we overlook? How many objects traverse our vicinity unnoticed because they are faint, their behavior is subtle, or we fail to observe them at the appropriate wavelengths? The answer is undoubtedly numerous. The cosmos is immense. Our surveys cover only portions of it at any given time, and small celestial bodies are challenging to track. Enhancing our detection capabilities, constructing more powerful telescopes, deploying more sensitive instruments, and employing artificial intelligence to analyze data all contribute to expanding our observational reach. Each improvement increases the probability of discovering more objects similar to 3 Atlas, or even stranger ones. With each new discovery, our classification of what constitutes normal expands. What once seemed impossible gradually becomes possible. What appeared unique becomes part of a recognizable pattern. This is the fundamental trajectory of scientific advancement, a progression from ignorance to partial understanding, and then to deeper comprehension, always provisional and subject to revision in light of new evidence. There is also a meta-level question concerning how science addresses the extraordinary. When confronted with an anomaly that challenges established assumptions, how do we strike a balance between skepticism and open-mindedness? Excessive skepticism may lead to the premature dismissal of genuine discoveries, while excessive openness can result in wasted effort on unfounded leads and pseudoscience. The peer review process, public discourse, and the replication of findings serve as safeguards, though they are not infallible. Careers, funding, and reputations are at stake, creating social pressures that can potentially compromise objectivity. 3 Atlas serves as a test case for these dynamics. Natural hypotheses represent the safer, more conventional explanations that align with existing scientific frameworks and are predisposed to community acceptance. Exotic hypotheses, conversely, are riskier, demanding more substantial evidence and facing greater hurdles for publication. Hypotheses invoking frontier physics are the most speculative, postulating new mechanisms that the majority of scientists consider improbable. Nevertheless, all 3 categories warrant careful consideration and evaluation based on their merits against the available data. The paramount challenge lies in maintaining this delicate equilibrium, avoiding both the premature rejection of ideas and their uncritical acceptance. For those observing from outside the scientific community, 3 Atlas serves as a potent reminder that the universe is replete with surprises, that our knowledge is inherently incomplete, and that the boundaries of the known are precisely where the most fascinating discoveries lie. It also underscores that science is fundamentally a human endeavor, shaped by the individuals who practice it, with all the creativity, biases, passions, and limitations that entails. We should celebrate the progress science achieves while acknowledging its imperfections. Therefore, as we conclude this exploration, here is a question to ponder moving forward. Are we observing not merely a comet, but a signal from something novel entering our solar neighborhood, something that defies our established categories, something that compels us to think more broadly and consider more unusual possibilities? Perhaps 3 Atlas is simply an unusual comet, ultimately natural in origin. Or perhaps it is something else entirely, a solar sail, a probe, a fragment of extraterrestrial engineering, or a manifestation of physics we have yet to comprehend. The current data does not definitively indicate which. However, the very fact that we are engaging with these questions seriously and rigorously is itself significant. The next 12 months will undoubtedly bring new observations, new analyses, and new debates. Stay informed. Follow the updates from JPL Horizons. Look for research papers from scientists studying 3-eye atlas. Listen to the discussions within the astronomical community. The narrative is still unfolding, and you are a witness to its real-time development. Science at its finest is a collective human endeavor to comprehend reality, and mysteries like 3 Atlas are precisely why that effort is so vital. We stand on the precipice, gazing at a visitor from the stars, attempting to decipher its secrets. It moves silently through the darkness, defying our expectations, whispering that the cosmos holds far more than we have ever imagined. Whether it represents a cosmic anomaly or a cosmic message, time and continued observation will reveal. But for now, we watch, we wonder, and we wait, knowing that the universe has surprised us before and will undoubtedly surprise us again. And with each surprise, we draw one step closer to understanding our place within the infinite expanse. The anomaly of 3 Atlas is not merely a scientific puzzle. It is an invitation to scrutinize more closely, to contemplate more deeply, and to maintain humility in the face of the vastness of our unknown. And that ultimately may be its most important lesson.